The James Webb Space Telescope was never supposed to start a scientific revolution. It was built for a far more conservative purpose, to extend the incredible success of the Hubble Space Telescope and strengthen the foundations of modern cosmology. For decades, astronomers believed they had assembled a remarkably accurate picture of how the universe began. The Big Bang Theory had survived every major challenge thrown at it. Observations of the expanding universe, the faint glow of the cosmic microwave background, the abundance of hydrogen and helium, and decades of increasingly sophisticated computer simulations all pointed toward the same conclusion. Nearly 14 billion years ago, the universe emerged from an unimaginably hot and dense state, expanded rapidly, cooled over billions of years, and slowly gave birth to the first stars, the first galaxies, and eventually everything we see today. The James Webb Space Telescope was designed to look farther back in time than ever before, not to rewrite that story, but to fill in its missing chapters. Scientists expected Webb to confirm their predictions with breathtaking detail. Instead, almost from the moment its first images arrived, the telescope began revealing a universe that looked strangely unfamiliar. The very first deep-field observations stunned astronomers around the world. Hidden inside what appeared to be tiny patches of empty darkness were thousands of galaxies stretching back almost to the dawn of cosmic history. That discovery alone was extraordinary. But it wasn't the number of galaxies that shocked researchers, it was their appearance. Many of them seemed far brighter, larger, and more mature than anyone had expected. According to decades of cosmological models, the universe was simply too young for galaxies like these to exist. They appear to have formed astonishingly quickly, as though billions of years of cosmic evolution had somehow been compressed in only a few 100 million years after the Big Bang. It was as if archaeologists digging into ancient history suddenly uncovered a modern skyscraper buried beneath the ruins of the first human villages. The discovery wasn't impossible, but it demanded an explanation. For more than 50 years, astronomers had refined their understanding of how galaxies grow. The process was believed to be gradual. Tiny fluctuations in the distribution of matter shortly after the Big Bang slowly attracted surrounding gas through gravity. Those clouds collapsed to form the first stars. Small galaxies merged together over hundreds of millions of years, becoming larger and more complex. Black holes formed within some of those galaxies and gradually increased in mass by consuming gas and merging with one another. Every stage of this process required time. In fact, time was the one resource the early universe simply didn't have. Yet Webb's observations seemed to suggest that nature had somehow accelerated the entire process beyond anything current models could comfortably explain. Then the surprises kept coming. Among Webb's most fascinating discoveries were mysterious objects that astronomers would eventually nickname the little red dots. These tiny crimson sources appeared across the earliest reaches of the observable universe. At first glance, they looked almost insignificant, small points of light hidden among countless distant galaxies. But as scientists studied them more carefully, they realized these objects might represent something far more profound. Some appeared too compact to be ordinary galaxies. Others were far brighter than expected. Spectroscopic observations hinted that many might contain rapidly growing supermassive black holes existing only a few 100 million years after the Big Bang. If that interpretation proved correct, it raised an unsettling question. How could black holes become so enormous in such a short period of cosmic history? The implications extended far beyond a handful of unusual observations. If Webb was accurately measuring these ancient objects, and there was every reason to believe it was, then some of the assumptions built into our models of the early universe might need serious revision. Scientists did not immediately declare the Big Bang Theory wrong. Science doesn't work that way. Instead, researchers began questioning every possible explanation. Could the distances be incorrect? Were the galaxies contaminated by foreground objects? Had the telescope introduced unexpected errors? Were existing computer simulations missing important physics? Every possibility had to be investigated before anyone could claim that the standard cosmological picture was incomplete. This cautious approach is one of science's greatest strengths. Extraordinary discoveries are not accepted simply because they are exciting. They must survive relentless testing from independent research teams around the world. Over the following months, astronomers repeatedly reanalyzed Webb's data using different techniques and different instruments. Additional observations confirmed many of the original measurements. While some early claims became more conservative as better data arrived, many of the broader mysteries refused to disappear. Again and again, Webb revealed galaxies that seemed unexpectedly evolved, black holes that appeared surprisingly massive, and structures that challenged long-standing expectations about the infinite universe. That is what makes this moment in astronomy so remarkable. The James Webb Space Telescope has not disproved the Big Bang, despite the sensational headlines that often circulate online. The overwhelming evidence that the universe expanded from an extremely hot and dense early state remains incredibly strong. But confirming the Big Bang and understanding everything that happened after it are two very different things. The standard model of cosmology contains many details about how the first stars formed, how galaxies assembled, and how black holes grew. It is these details, not necessarily the existence of the Big Bang itself, that Webb has begun placing under unprecedented pressure. History shows that this is often how scientific revolutions begin. They rarely start with a single observation that instantly destroys an established theory. Instead, they begin with small anomalies, tiny pieces of evidence that don't quite fit. At first, those anomalies are usually dismissed as measurement errors or statistical accidents. But if they continue appearing in independent observations, they gradually force scientists to ask deeper questions. Sometimes the existing theory survives with only minor adjustments. Other times, those anomalies become the first cracks in an intellectual framework that once seemed unshakable. No one yet knows which path the James Webb Space Telescope will ultimately lead us down. What makes this story even more compelling is that Webb was specifically engineered to answer these questions. Its enormous gold-coated mirror, its ultra-sensitive infrared instruments, and its position nearly 1.5 million kilometers from Earth allow it to observe light that has traveled across more than 13 billion years of cosmic history. Every photon collected by the telescope is effectively a message from the distant past. When Webb peers deeper into space, it is also looking farther back in time, allowing humanity to witness the universe as it existed long before our own galaxy, our own sun, or even our own planet had formed. Never before have astronomers possessed such a powerful machine for exploring the earliest chapters of cosmic history. And yet, instead of quietly confirming everything researchers expected to find, the telescope has become the source of some of the biggest debates in modern astronomy. Around the world, research groups are racing to explain these unexpected discoveries. Some believe the answers lie in new models of galaxy formation. Others argue that black holes may have grown through processes never fully considered before. A few researchers have even suggested that certain aspects of our cosmological framework may require substantial revision. Whatever the final answer proves to be, one thing has become increasingly clear. The James Webb Space Telescope was built to confirm humanity's understanding of the universe. Instead, it has reminded us that the universe still has the power to surprise us. The Big Bang is often described as the moment the universe began. It has become one of the most famous scientific theories ever developed, recognized far beyond the world of astronomy and physics. Yet despite its popularity, it is also one of the most misunderstood ideas in modern science. Many people imagine the Big Bang as a gigantic explosion, a colossal fireball erupting into an empty void, sending matter flying outward in every direction. Movies, television programs, and even some textbooks have reinforced this image for decades. But according to modern cosmology, that is not what the Big Bang actually describes. There was no explosion in space because there was no empty space waiting to be filled. Instead, space itself expanded. Every region of the universe began stretching simultaneously, carrying galaxies farther apart as the fabric of space-time itself grew larger. It is a subtle distinction, but one that changes everything. The standard cosmological model tells a remarkably elegant story. Around 13.8 billion years ago, the observable universe existed in an unimaginably hot, incredibly dense state. Physicists often describe this beginning as a singularity, although that word can be misleading. A singularity is not something we can directly observe. Rather, it is a mathematical indication that our current understanding of physics breaks down under such extreme conditions. It represents a point where density, temperature, and curvature approach values that our equations can no longer properly describe. In other words, the singularity is less a physical object than a signpost telling scientists that a deeper theory of nature remains undiscovered. From that extraordinary beginning, the universe entered an era of rapid expansion. During an unimaginably tiny fraction of a second, space itself expanded at an astonishing rate in an event known as cosmic inflation. This brief period smoothed out the young universe, explaining why the cosmos appears remarkably uniform in every direction today. Tiny quantum fluctuations that existed during inflation were stretched across enormous distances, eventually becoming the seeds from which galaxies, galaxy clusters, and the vast cosmic web would later emerge. Every star, every planet, every black hole, and every living creature can ultimately trace its origins back to those microscopic fluctuations present in the earliest moments of cosmic history. As the universe expanded, it also cooled. In its earliest moments, temperatures were so extreme that matter, as we know it, simply could not exist. Protons and neutrons collided constantly with an ocean of radiation, preventing stable atoms from forming. Gradually, however, the cosmos cooled enough for the first atomic nuclei to appear through a process called Big Bang nucleosynthesis. During this brief period, the universe produced enormous quantities of hydrogen, along with smaller amounts of helium and tiny traces of lithium. Remarkably, modern observations still match these predicted abundances with impressive accuracy. This agreement became one of the strongest pieces of evidence supporting the Big Bang theory and convinced generations of astronomers that they were looking at a fundamentally correct picture of cosmic history. Hundreds of thousands of years later, another crucial milestone occurred. The universe had expanded and cooled enough for electrons to combine with atomic nuclei, forming the first neutral atoms. Before this moment, free electrons scattered light in every direction, making the universe opaque, almost like the dense interior of a cloud. Once neutral atoms formed, light could finally travel freely through space. That ancient light has continued its journey for nearly 14 billion years and can still be detected today as the cosmic microwave background, often described as the oldest light in the universe. Its discovery in 1965 transformed cosmology. Suddenly, scientists possessed direct observational evidence of a hot early universe exactly as the Big Bang theory predicted. Over the following decades, additional discoveries continued strengthening the model. Edwin Hubble's observation that distant galaxies are moving away from one another demonstrated that the universe is expanding. Measurements of the cosmic microwave background revealed tiny temperature variations that perfectly matched theoretical predictions for the seeds of future galaxies. Large-scale galaxy surveys showed a cosmic web remarkably similar to computer simulations based on the Big Bang model. Every major observation appeared to reinforce the same overall picture. The theory became so successful that many scientists considered it the foundation upon which all modern cosmology rested. Yet success sometimes creates confidence, and confidence can gradually become assumption. As computer simulations became increasingly sophisticated, astronomers developed a detailed timeline describing exactly how the early universe should evolve. According to these models, the first stars should appear after a few 100 million years. Small galaxies would gradually assemble from those stars. Over immense periods of time, mergers between galaxies would create larger structures. Supermassive black holes would slowly grow through steady accretion and repeated collisions, eventually reaching the enormous masses observed in nearby galaxies today. Every stage of this evolutionary process depended on one crucial ingredient: time. The universe could only build complexity gradually. There were limits to how quickly gravity could pull matter together, how rapidly stars could form, and how efficiently black holes could accumulate mass. These limits were not arbitrary. They were grounded in the known laws of physics and supported by decades of observations. The standard cosmological model did not merely explain where the universe came from. It also predicted what the young universe should look like at different stages of its evolution. That predictive power became one of its greatest strengths. If you pointed a sufficiently powerful telescope toward the earliest galaxies, the models suggested you would find small, irregular systems just beginning their long journey toward becoming the giant spiral and elliptical galaxies we see today. Their stars would still be relatively young. Their chemical composition would remain simple because only a few generations of stars had existed to manufacture heavier elements. Their central black holes, if present at all, would still be relatively modest in size. In many ways, astronomers believed they already knew what the James Webb Space Telescope was going to find before it ever launched. Webb was expected to provide breathtaking confirmation. Instead, it delivered breathtaking questions. Almost immediately after the telescope began observing the distant universe, researchers noticed objects that seemed to violate those carefully constructed expectations. Some galaxies appeared far brighter than predicted. Others seemed astonishingly massive despite existing only a few 100 million years after the Big Bang. The mysterious little red dots hinted at supermassive black holes growing far faster than current theories allowed. Individually, each observation could perhaps be explained through revised measurements or improved simulations. Collectively, however, they pointed toward a growing tension between theory and observation. This does not necessarily mean the Big Bang itself is wrong. In fact, most cosmologists continue to regard the evidence for an expanding, hot early universe as overwhelming. The expansion of galaxies, the cosmic microwave background, and the observed abundance of light elements remain among the strongest pillars of modern science. But those pillars support a much larger structure filled with assumptions about how galaxies formed, how quickly stars evolved, how black holes accumulated mass, and how the first billion years of cosmic history unfolded. It is within those details that the James Webb Space Telescope has begun exposing unexpected cracks. History reminds us that science evolves not by abandoning successful theories at the first sign of trouble, but by investigating anomalies with patience and skepticism. Sometimes those anomalies disappear as new data improves our understanding. Other times, they reveal entirely new layers of reality that previous generations could never have imagined. Today, astronomers find themselves standing at exactly that crossroads. The Big Bang remains one of the greatest scientific achievements ever developed, but the universe revealed by the James Webb Space Telescope appears more complicated, more mature, and perhaps more surprising than the elegant story scientists have been telling for the past 50 years. The question is no longer whether the Big Bang happened. The question is whether we have truly understood everything that happened after it. For decades, astronomers believed they had a reliable timeline for how the universe grew from a nearly uniform sea of hot plasma into the vast cosmic landscape we see today. According to the standard model of cosmology, the first few 100 million years after the Big Bang were a slow and delicate period of construction. Gravity was only beginning to gather enormous clouds of hydrogen and helium into the first dark matter halos. Inside those halos, the earliest stars ignited, flooding the young universe with light for the very first time. Those primitive stars gradually assembled into tiny, irregular galaxies. Over hundreds of millions and eventually billions of years, these small galaxies merged together, becoming larger, brighter, and increasingly complex. Every modern simulation told the same story. The early universe was expected to be messy, chaotic, and immature. Large spiral galaxies like the Milky Way were not supposed to exist. Massive elliptical galaxies were not supposed to exist. Bright, chemically evolved systems were certainly not supposed to exist. At least, not so early in cosmic history. This expectation wasn't based on guesswork. It was the result of decades of increasingly sophisticated computer simulations that incorporated gravity, gas dynamics, star formation, dark matter, black hole growth, and the expansion of the universe itself. Some of the most advanced simulations ever created, projects like Illustris, Eagle, and Millennium, were remarkably successful at reproducing the modern universe. They generated galaxies that closely resembled those observed by telescopes, predicted the large-scale cosmic web with impressive accuracy, and explained countless astronomical observations. Because these models had proven themselves repeatedly, astronomers approached the James Webb Space Telescope with considerable confidence. Webb wasn't expected to rewrite the timeline of galaxy formation. It was expected to provide the clearest confirmation, yet that those simulations had been right all along. Then the telescope began sending back its first images. Among the earliest observations was Webb's famous deep field, an image that looked almost magical. What appeared from Earth to be an almost empty patch of sky suddenly exploded into view as a breathtaking landscape filled with thousands of galaxies. Every tiny speck of light represented an entire galaxy, many containing billions of stars. Some were so distant that their light had traveled for more than 13 billion years before finally reaching Webb's enormous golden mirror. Looking at that image was like looking through a time machine, allowing humanity to witness the universe during its earliest stages of existence. At first, astronomers simply admired the extraordinary detail. Webb had exceeded expectations in terms of image quality. But as researchers began carefully measuring the properties of those distant galaxies, excitement gradually turned into confusion. Many of them looked wrong. Not wrong because the telescope had malfunctioned. Wrong because the galaxies themselves seemed to ignore everything the standard cosmological timeline predicted. Some of these galaxies appeared surprisingly large. Others seemed unexpectedly bright. Even more astonishing, several displayed structures and stellar populations suggesting that they had already undergone extensive periods of evolution. Instead of looking like newborn galaxies only beginning to assemble, they looked surprisingly mature, almost as though they had already spent billions of years growing and evolving. But there was an obvious problem. The universe simply wasn't old enough. Some of these galaxies existed only around 300 million years after the Big Bang. To appreciate how astonishing that is, imagine compressing the entire 13.8 billion-year history of the universe into a single calendar year. In that scale, these galaxies would appear during the first few days of January. Yet they already seemed comparable, in some respects, to systems that conventional models predicted should not emerge until much later in cosmic history. Astronomers immediately began searching for mistakes. Perhaps Webb had overestimated their brightness. Perhaps dust had altered their colors. Perhaps the galaxies were actually closer than they appeared. Distance measurements in astronomy are notoriously difficult, especially when observing objects billions of light years away. Because the universe is expanding, light from distant galaxies becomes stretched toward longer wavelengths, a phenomenon known as cosmological redshift. Webb's infrared instruments were specifically designed to detect this stretched light. By measuring the redshift, astronomers could estimate how far away these galaxies were and therefore how early they existed in cosmic history. Initially, some scientists wondered whether the first distance estimates might be inaccurate. It was a reasonable concern. Early observations often contain uncertainties that are resolved as additional data becomes available. Over the following months, however, Webb continued observing many of these galaxies using spectroscopy, one of the telescope's most powerful capabilities. Instead of relying solely on brightness and color, spectroscopy analyzes the unique fingerprints of light emitted by different elements. These measurements provided much more reliable estimates of cosmic distance. Again and again, The results pointed toward the same conclusion. Many of these galaxies really were extraordinarily ancient. The measurements became increasingly difficult to dismiss. That realization forced astronomers to confront a far more uncomfortable possibility. Perhaps the problem wasn't the telescope. Perhaps the problem was the models. If these galaxies truly existed only a few 100 million years after the Big Bang, then they must have formed stars at incredible speeds. Some estimates suggested star formation rates several times higher than current theories considered realistic. Entire populations of stars appeared to emerge with astonishing efficiency, converting enormous clouds of primordial gas into mature galaxies in what seemed like a cosmic instant. How could this happen? Gravity certainly pulls matter together, but gravity also works slowly across astronomical distances. Gas clouds must cool before collapsing into stars. Those stars require time to produce heavier elements through nuclear fusion, exploding supernovae enrich surrounding gas, allowing later generations of stars and planets to form. Every stage introduces delays. According to conventional theory, building a large galaxy should be a gradual process stretching across hundreds of millions or even billions of years. Yet Webb appeared to be showing galaxies that had somehow skipped much of that timeline. Some researchers propose that the earliest stars may have been far more massive than previously believed. Massive stars burn through their nuclear fuel extremely quickly, living only a few million years before exploding as supernovae. If the first generation of stars formed unusually efficiently, they might have accelerated the chemical evolution of the young universe far beyond existing predictions. Others suggested that galaxies in the early universe experienced intense bursts of star formation unlike anything commonly observed today. Instead of slowly producing stars over billions of years, these primordial systems may have converted gas into stars with extraordinary efficiency during relatively brief periods of cosmic history. Another possibility focused on dark matter. Dark matter makes up most of the universe's mass, yet remains invisible because it does not emit or absorb light. Its gravity acts as the scaffolding upon which galaxies form. If dark matter behaved even slightly differently during the universe's earliest epochs than current models assume, it could potentially accelerate galaxy formation in ways that existing simulations fail to reproduce. Some theorists even revisited the physics of cosmic inflation and the tiny density fluctuations produced immediately after the Big Bang. Perhaps those fluctuations were larger in certain regions than scientists had realized, creating pockets of the universe where galaxies assembled unusually quickly. Each explanation offered hope. Each also introduced new questions. None fully solved the mystery. Meanwhile, the discoveries continued. With every new observing program, Webb identified additional candidate galaxies from the first few 100 million years of cosmic history. Some previous estimates became more conservative after improved measurements, but the broader pattern refused to disappear. The early universe consistently appeared richer, brighter, and more evolved than expected. Importantly, this does not mean the Big Bang itself has been disproven. That distinction is absolutely essential. The expanding universe remains one of the strongest observational facts in modern astronomy. The cosmic microwave background still provides extraordinary evidence for a hot early universe. The abundance of hydrogen and helium continues matching Big Bang predictions with remarkable precision. None of these pillars have collapsed. Instead, what Webb has challenged is the detailed story of what happened next. How quickly did the first stars form? How rapidly did galaxies assemble? How efficiently could primordial gas collapse under gravity? Could black holes have accelerated galaxy evolution? Or are entirely new physical processes waiting to be discovered? These are the questions now driving one of the most exciting periods in modern cosmology. Because if the earliest galaxies truly matured far faster than anyone believed possible, then humanity may not need to rewrite the beginning of the universe. But we may need to rewrite its childhood. The discovery of surprisingly mature galaxies was only the beginning of the mystery. Their appearance alone was enough to make astronomers question whether something important had been overlooked. But as researchers measured these galaxies more carefully, another problem emerged, one that was even harder to explain. It wasn't simply that these galaxies looked older than expected. They also appeared far too massive. According to some of the earliest measurements from the James Webb Space Telescope, certain galaxies that existed only a few 100 million years after the Big Bang seem to contain billions of stars. In some cases, their estimated stellar masses rival galaxies that, according to standard cosmological models, should have required billions of years to assemble. It was as though nature had somehow skipped vast portions of cosmic history, producing enormous galaxies almost immediately after the universe began. To understand why this is so surprising, imagine trying to build an entire modern city from scratch. First, raw materials must be gathered. Roads need to be laid, buildings constructed, power grids installed, and infrastructure gradually expanded over decades. Even with unlimited resources, the process cannot happen instantly because every stage depends upon the completion of the one before it. The early universe faced a similar challenge. Before galaxies could become massive, hydrogen and helium gas first needed to collect inside invisible halos of dark matter. Those gas clouds then had to cool, collapse under gravity, ignite nuclear fusion, produce the first generations of stars, enrich surrounding space with heavier elements through supernova explosions, and continue forming new stars over immense stretches of time. Every one of these steps takes time, and according to every major cosmological simulation developed over the last several decades, there simply was not enough time available. The James Webb Space Telescope changed that assumption almost overnight. Instead of finding tiny, lightweight galaxies just beginning to emerge from the cosmic darkness, Webb detected objects whose estimated masses seemed astonishingly large. Some analyses suggested stellar masses approaching 10 billion times the mass of our Sun only 300 to 500 million years after the Big Bang. While later observations refined several of those estimates downward, the broader tension remained. Even the revised measurements often described galaxies significantly more massive than theorists had expected. The problem was no longer limited to one unusual object. Similar candidates continued appearing across multiple observing programs, suggesting that these surprisingly massive galaxies might not be rare exceptions, but part of a broader population in the young universe. At first, astronomers suspected the measurements themselves might be misleading. Estimating the mass of a galaxy that lies more than 13 billion light-years away is an extraordinarily difficult task. Scientists cannot place such galaxies on scales or directly count every individual star. Instead, they estimate stellar mass by analyzing the light the galaxy emits. The brightness, color, and spectrum of that light reveal clues about how many stars are present, how old those stars are, and how much matter they likely contain. But these calculations depend on assumptions about stellar populations, dust content, and the history of star formation. If any of those assumptions were incorrect, the estimated masses could be significantly overestimated. This possibility encouraged researchers to remain cautious. As additional observations accumulated, some of the earliest galaxies originally believed to be extraordinarily massive were indeed revised downward. Better spectroscopy revealed that a number of candidates were somewhat closer than initially estimated, reducing their inferred brightness and therefore their calculated stellar mass. Yet despite these corrections, the underlying problem refused to disappear completely. Even after applying more conservative measurements, many galaxies still appeared substantially larger and more evolved than standard models comfortably predicted. The numbers improved, but the tension remained. Dark matter quickly became central to the discussion. Although invisible, dark matter makes up roughly 85% of all matter in the universe. It does not emit light, absorb radiation, or interact strongly with ordinary atoms, but its gravity shapes the large-scale structure of the cosmos. Long before the first stars formed, dark matter began collapsing into enormous halos that acted as gravitational wells, pulling ordinary gas inward. Every modern theory of galaxy formation depends on these halos. Without dark matter, galaxies would struggle to form at all. Because dark matter plays such an important role, some astronomers wondered whether existing simulations underestimated how efficiently it gathered matter during the universe's earliest epochs. Perhaps the first dark matter halos formed more rapidly than expected. Perhaps they attracted gas with greater efficiency under the unique conditions of a young universe. If so, galaxies could begin assembling earlier than conventional models predicted. But even this explanation encountered significant difficulties. Dark matter can create the gravitational framework for galaxies, yet it cannot directly produce stars. Ordinary gas must still cool, fragment, and collapse before stellar populations can emerge. Gravity alone cannot eliminate every bottleneck in the process. Another possibility focused on the first generation of stars, known as population 3 stars. These primordial stars were unlike anything commonly seen today. Because the early universe contained almost no heavy elements, theoretical models suggest these stars may have grown far larger than modern stars, perhaps reaching hundreds of times the mass of the Sun. Massive stars burn through their nuclear fuel extremely quickly, living only a few million years before exploding as supernovae. If the earliest galaxies formed unusually large numbers of these gigantic stars, they might have produced tremendous amounts of light while rapidly enriching surrounding gas with heavier elements that could accelerate subsequent generations of star formation, helping galaxies mature much faster than standard simulations currently predict. While attractive, this explanation also raises new questions. Producing enough massive stars to explain Webb's observations requires remarkably efficient star formation across enormous regions of space. Existing models struggle to achieve such efficiencies naturally. Moreover, many of the galaxies observed by Webb appear not only bright, but structurally developed, suggesting that star formation alone may not fully explain their apparent maturity. Some researchers proposed an even more intriguing possibility. Perhaps astronomers have misunderstood how efficiently gas behaved in the early universe itself. Conditions shortly after the Big Bang were fundamentally different from those in today's cosmos. The chemical composition was simpler. Temperatures were higher. Radiation fields were more intense. Under those unique circumstances, gas clouds may have cooled, collapsed, and converted into stars through mechanisms not fully captured by existing simulations. If true, the early universe may have been capable of building galaxies with astonishing speed, not because the laws of physics were different, but because the environment favored processes rarely observed today. Others looked toward the influence of supermassive black holes. Modern galaxies often host enormous black holes at their centers, and these objects profoundly influence their surroundings. Material falling into a black hole releases extraordinary amounts of energy, capable of regulating star formation, driving powerful outflows, and reshaping entire galaxies. If massive black holes formed much earlier than expected, they may have accelerated certain aspects of galaxy evolution in ways current models have underestimated. Ironically, the same mysterious little red dots discussed earlier may eventually become part of the solution to the mass problem. If many of those objects are actively feeding supermassive black holes, they could represent evidence that black hole growth and galaxy formation occurred simultaneously at far greater speeds than anyone anticipated. Still, none of these explanations has yet solved the puzzle completely. Every proposed solution appears capable of explaining part of the evidence while introducing new challenges elsewhere. Accelerating star formation may produce more massive galaxies, but it must remain consistent with observations of chemical abundances. Increasing the efficiency of dark matter collapse affects the entire large-scale structure of the universe, which already matches observations remarkably well. Earlier black hole formation may explain rapid galaxy evolution, but then researchers must explain how those black holes themselves became so enormous in such a short period of time. Each answer seems to create another mystery. This is precisely why the James Webb Space Telescope has generated so much excitement within the astronomical community. Scientific revolutions rarely begin with dramatic declarations that everything we know is wrong. Instead, they begin with persistent inconsistencies, observations that refuse to disappear despite increasingly careful measurements. The mass problem has become one of those inconsistencies. It does not necessarily invalidate the Big Bang, nor does it prove that decades of cosmological research were fundamentally mistaken. Rather, it suggests that the story of the universe's earliest few hundred million years may be far more dynamic than scientists once imagined. Perhaps galaxies assembled with astonishing efficiency under conditions unique to the primordial cosmos. Perhaps dark matter behaves in subtle ways that current simulations have not yet captured. Perhaps the first stars were more powerful than any we see today. Or perhaps entirely new physics awaits discovery beyond the limits of our existing theories. Whatever the answer ultimately proves to be, one conclusion has already become difficult to ignore. The earliest galaxies were not supposed to become this massive this quickly. Yet the James Webb Space Telescope continues to show us that the universe often follows its own timetable rather than ours. Every new observation pushes astronomers to reconsider assumptions once regarded as settled, reminding us that the cosmos is not obligated to match our expectations. Instead, it reveals its history one photon at a time. And those ancient photons are beginning to tell a story far more surprising than anyone expected when the James Webb Space Telescope first unfolded its golden mirror beneath the darkness of space. For much of modern astronomy, spiral galaxies have been regarded as one of the universe's greatest long-term achievements. Their graceful, sweeping arms stretching outward from bright central bulges are among the most recognizable structures in the cosmos. Our own Milky Way is a magnificent barred spiral galaxy, containing hundreds of billions of stars arranged in an intricate pattern that has taken billions of years to develop. These elegant cosmic structures are so familiar that it is easy to forget just how difficult they are to create. According to everything astronomers believed before the launch of the James Webb Space Telescope, spiral galaxies were never expected to appear in the earliest chapters of cosmic history. They were thought to be the end result of an incredibly long evolutionary journey, a journey requiring countless generations of stars, repeated mergers, stable gravitational interactions, and immense amounts of time. Yet once again, Webb looked into the distant universe and revealed something that seemed impossible. It discovered surprisingly well-formed spiral galaxies existing far earlier than anyone had imagined, raising another profound question. If these galaxies already possessed organized spiral structures billions of years ago, then how quickly did the universe really evolve after the Big Bang? To appreciate why this discovery generated so much excitement, it helps to understand what makes spiral galaxies so remarkable. They are not simply random collections of stars scattered through space. Every spiral arm represents an enormous wave of stars, gas, and dust moving through the galaxy under the influence of gravity. Those elegant patterns emerge from an incredibly delicate balance between rotational motion, dark matter, star formation, and gravitational interactions. Building such an organized system is extraordinarily complex. Newly formed galaxies are expected to be turbulent environments filled with violent bursts of star formation, frequent collisions with neighboring galaxies, and enormous clouds of gas moving chaotically in every direction. Over immense stretches of time, those chaotic systems gradually settle into more stable rotating disks. Only then can the familiar spiral patterns begin to emerge. That gradual transformation has been one of the cornerstones of galaxy evolution models for decades. Computer simulations consistently showed that the earliest galaxies should look irregular and clumpy. Rather than displaying smooth, symmetrical spiral arms, they were expected to resemble distorted collections of bright star-forming regions connected by unstable streams of gas. Every major merger between galaxies would temporarily disrupt their structure, forcing them to begin the slow process of stabilization all over again. Because the young universe experienced mergers far more frequently than today's relatively peaceful cosmos, astronomers assumed that beautiful spiral galaxies would be extremely rare during the first few billion years of cosmic history. The Hubble Space Telescope appeared to support this picture. Although Hubble captured extraordinary images of distant galaxies, its ability to observe the earliest universe was limited by both its mirror size and its sensitivity to infrared light. The farther astronomers looked into space, the younger and more chaotic galaxies appeared. This reinforced confidence in existing models. The timeline seemed straightforward. Small, irregular galaxies formed first. Gradually, they merged into larger disks. Eventually, after billions of years of gravitational evolution, majestic spiral galaxies emerged. It was a simple, elegant sequence that fit comfortably within the standard picture of cosmic evolution. Then the James Webb Space Telescope began looking deeper than Hubble had ever been capable of seeing. Because Webb observes primarily in infrared wavelengths, it could detect light that has been stretched by the expansion of the universe over billions of years. This allows astronomers to examine galaxies that existed when the universe was still remarkably young. Scientists expected these observations to reveal primitive systems only beginning their evolutionary journey. Instead, Webb started uncovering galaxies with surprisingly recognizable spiral structures at distances corresponding to more than 11 billion years into the past. Some observations even suggested disk-like galaxies forming earlier than theoretical models had predicted possible. The reaction among astronomers was immediate. How could galaxies become this organized so quickly? Forming spiral arms is not simply a matter of collecting enough stars. Spiral structure depends upon the stability of an entire galactic disk. Gas must settle into orderly rotation. Gravitational instabilities must develop in very specific ways. Star formation must proceed without completely disrupting the delicate balance of the system. Even relatively minor interactions with neighboring galaxies can distort or destroy spiral patterns. In the crowded environment of the young universe, where mergers occurred frequently, maintaining such organized structures should have been extraordinarily difficult. Yet there they were. Some of Webb's images revealed galaxies displaying surprisingly symmetrical disks, central bulges, and visible spiral features that looked remarkably similar to systems found much closer to the present day. They were not necessarily identical to the mature spirals surrounding the Milky Way today, but they were far more developed than existing simulations had predicted. Naturally, astronomers first questioned whether these objects truly were spiral galaxies. Perspective can be deceptive in astronomy. A galaxy viewed from certain angles may appear more organized than it actually is. Dust, brightness, and observational limitations can also create misleading impressions. Researchers therefore analyzed the images carefully, comparing them with computer simulations and alternative structural models. As additional observations accumulated, confidence grew that at least many of these objects genuinely possessed rotating disk-like structures with spiral characteristics. If confirmed, the implications were profound. The discoveries suggested that galaxies may settle into stable rotational disks much earlier than current theories predict. Rather than spending billions of years gradually transitioning from chaotic systems into organized spirals, some galaxies may have completed much of that transformation within a surprisingly short period after the Big Bang. Several explanations quickly emerged. One possibility was that the earliest galaxies contained enormous amounts of cold gas capable of collapsing efficiently into rapidly rotating disks. Under the unique physical conditions of the early universe, gravity may have organized matter much faster than current simulations allow. If gas cooled more efficiently than expected, galaxies could stabilize relatively quickly despite their violent surroundings. Another explanation focused on the role of dark matter. Invisible dark matter halos provide the gravitational framework around which galaxies form. If those halos developed particularly favorable shapes or rotational properties during the universe's earliest epochs, they might have encouraged the formation of stable galactic disks much sooner than standard models predict. This idea remains an active area of research because dark matter itself remains one of astronomy's greatest unsolved mysteries. Some researchers suggested that computer simulations may simply underestimate the complexity of feedback processes inside young galaxies. Massive stars release tremendous amounts of energy through stellar winds and supernova explosions. Black holes inject additional energy into their surroundings as they consume matter. These processes can both disrupt and regulate galaxy evolution. If simulations fail to capture those interactions accurately, they may produce unrealistic timelines for spiral galaxy formation. Interestingly, not every astronomer interprets Webb's observations as evidence that current cosmology is fundamentally broken. Many researchers argue that while the discoveries are surprising, they remain compatible with the Big Bang once galaxy formation models are refined. In this view, Webb is not overturning cosmology, but revealing that the physics governing the earliest galaxies is more efficient and more complicated than previously understood. Others remain less convinced. They argue that when considered alongside Webb's other discoveries, unexpectedly massive galaxies, surprisingly early supermassive black holes, mysterious little red dots, and mature galactic populations appearing far earlier than anticipated, a consistent pattern begins to emerge. Individually, each anomaly might be explained through adjustments to existing models. Collectively, however, they seem to suggest that the young universe was evolving at a pace that current theories struggle to reproduce. This is precisely why the James Webb Space Telescope has generated so much excitement throughout the scientific community. Every unexpected discovery forces astronomers to revisit assumptions that once seemed secure. The telescope is not simply collecting beautiful photographs. It is testing decades of theoretical predictions against the actual history of the universe. Perhaps spiral galaxies really can form much faster than anyone imagined. Perhaps conditions shortly after the Big Bang favored rapid organization under physical processes we have only begun to understand. Or perhaps these elegant cosmic structures are quietly pointing toward an even deeper mystery, one that reaches beyond galaxy formation itself and into the fundamental laws governing the evolution of the universe. Whatever the final explanation proves to be, one fact is becoming increasingly difficult to ignore. The universe that James Webb is revealing does not behave quite the way scientists expected. Time after time, observations continue showing galaxies that appear older, larger, more massive, and more organized than the standard timeline predicts. The graceful spiral arms stretching across these ancient galaxies are more than beautiful cosmic artwork. They are silent evidence that the early universe may have been capable of building complexity far faster than humanity had believed possible. And if galaxies were already achieving this level of organization billions of years earlier than expected, then perhaps the history of the cosmos is not as simple or as complete as we once thought. The history of modern cosmology is filled with remarkable successes. Over the past century, astronomers have measured the age of the universe, mapped billions of galaxies, detected the faint afterglow of the Big Bang, and even observed gravitational waves produced by colliding black holes. Piece by piece, humanity has assembled what appears to be an extraordinarily detailed picture of cosmic history. Yet among all these achievements, one problem has quietly refused to disappear. It is not as visually spectacular as a black hole or as dramatic as an exploding supernova. Instead, it is hidden inside numbers that should agree with one another, but stubbornly refuse to do so. This mystery has become known as the Hubble Tension, and today many astronomers consider it one of the greatest unsolved problems in cosmology. Unlike many scientific disagreements that eventually disappear with better observations, this one has only grown stronger with time. What was once dismissed as a possible measurement error has gradually evolved into evidence that something important may be missing from our understanding of the universe itself. To appreciate why this problem is so significant, we first need to understand one of the most fundamental discoveries in astronomy. In the late 1920s, Edwin Hubble demonstrated that distant galaxies are moving away from us. More importantly, he found that the farther away a galaxy is, the faster it appears to be receding. This simple relationship revealed that the universe is expanding. Imagine drawing dots across the surface of an uninflated balloon. As the balloon expands, every dot moves away from every other dot. No single dot sits at the center of the expansion. Instead, the space between all of them stretches simultaneously. The universe behaves in much the same way. Galaxies are not simply flying through empty space. Rather, space itself is expanding, carrying galaxies farther apart over billions of years. Astronomers describe the speed of this expansion using a quantity known as the Hubble constant. Despite its name, it is not truly constant throughout the history of the universe. Instead, it represents the current rate at which the cosmos is expanding. It is usually expressed in kilometers per second per megaparsec. While the units may sound intimidating, the idea is surprisingly simple. If the Hubble constant is 70 kilometers per second per megaparsec, then for every megaparsec of distance, about 3.26 million light-years, a galaxy appears to move away approximately 70 kilometers per second faster. Double the distance, and the recession speed roughly doubles as well. Triple the distance, and it increases again. This relationship has become one of the cornerstones of modern cosmology. For decades, scientists believed that improvements in technology would gradually refine this number until everyone agreed on its exact value. After all, every new telescope offered more accurate observations, and every generation of astronomers developed better methods for measuring cosmic distances. It seemed only a matter of time before the uncertainty disappeared. Instead, the opposite happened. As observations became more precise, two completely independent techniques began producing two completely different answers. The first method looks deep into the early universe. Rather than measuring nearby galaxies directly, it examines the cosmic microwave background, the faint radiation left over from roughly 380,000 years after the Big Bang. This ancient light acts almost like a photograph of the infant universe. Tiny fluctuations imprinted within it reveal information about the universe's composition, density, and geometry. By combining these observations with the standard model of cosmology, scientists can calculate what today's expansion rate should be. Measurements from missions, such as the Planck satellite, consistently produce a value of approximately 67 kilometers per second per megaparsec. The calculations are extraordinarily precise, with remarkably small uncertainties. The second approach could hardly be more different. Instead of looking nearly 14 billion years into the past, astronomers measure the expansion of the nearby universe directly. They build what is known as the cosmic distance ladder, an ingenious sequence of overlapping techniques used to determine the distances to increasingly remote galaxies. The process begins with nearby stars whose distances can be measured through parallax as Earth orbits the Sun. Those stars calibrate Cepheid variable stars, remarkable objects whose brightness changes in predictable ways. Cepheids then calibrate type Ia supernovae, brilliant stellar explosions visible across enormous cosmic distances. By comparing the true brightness of these objects with how bright they appear from Earth, astronomers determine their distances. Combined with measurements of galactic recession velocities, these observations yield a direct estimate of the Hubble constant. Again and again, this completely independent method arrives at essentially the same answer: approximately 73 kilometers per second per megaparsec. At first glance, the difference may appear trivial. 67 versus 73. Only 6 units apart. In everyday life, such a small discrepancy might seem meaningless. In precision cosmology, however, it is enormous. Modern astronomical observations have become so accurate that these two values should overlap if the standard cosmological model is complete. Instead, they remained stubbornly separated. As measurement techniques improved, uncertainties shrank, yet the disagreement persisted. Rather than converging toward a single answer, the two methods continued pointing toward two different universes. Initially, astronomers assumed someone had simply made a mistake. Perhaps nearby galaxies contained hidden sources of dust affecting brightness measurements. Perhaps Cepheid variables behaved differently than expected. Maybe the Planck satellite had introduced subtle calibration errors. Perhaps computer models describing the early universe overlooked some systematic effect. Every conceivable source of observational error became the subject of careful investigation. Research teams around the world independently repeated the measurements using different telescopes, different calibration techniques, and entirely different statistical methods. The result was deeply unsettling. The disagreement refused to disappear. Today, the statistical significance of the Hubble tension has reached approximately 5 sigma, the same level of confidence physicists generally require before claiming a genuine discovery. In practical terms, a 5 sigma result means the probability that this discrepancy exists purely because of random chance is extraordinarily small. In particle physics, this standard was used to confirm the discovery of the Higgs boson. In cosmology, reaching 5 sigma suggests the Hubble tension is no longer simply an experimental curiosity. It is a real physical problem demanding explanation. If both measurement techniques are correct, then something fundamental may be missing from our picture of the universe. One possibility is that the standard cosmological model requires new physics operating shortly after the Big Bang. Some researchers have proposed a brief period of early dark energy, an additional form of energy that temporarily accelerated expansion before disappearing. Others have suggested previously unknown particles interacting with ordinary matter during the universe's infancy. Some theories even explore subtle modifications to Einstein's theory of gravity itself. Each proposal attempts to reconcile the two conflicting expansion rates without contradicting the many other successful predictions of modern cosmology. None has yet emerged as the definitive solution. Interestingly, the arrival of the James Webb Space Telescope has not solved the Hubble tension. If anything, Webb has strengthened confidence in the direct measurements. Its extraordinary infrared vision allows astronomers to observe Cepheid variable stars with far greater clarity than ever before, reducing uncertainties caused by interstellar dust and crowded stellar environments. Early Webb observations have broadly supported the local expansion rate rather than eliminating the discrepancy. While the debate continues, the telescope has made it increasingly difficult to dismiss the tension as a simple calibration error. This places cosmologists in a fascinating position. At the same time that Webb is discovering unexpectedly massive galaxies, surprisingly mature spiral structures, rapidly growing supermassive black holes, and mysterious little red dots in the infant universe, one of the most important numbers in cosmology also refuses to behave as expected. Individually, each anomaly can perhaps be explained through adjustments to existing models. Together, however, they paint a picture of a universe that may be more complicated than the elegant story scientists believe they had completed. The Hubble tension does not prove that the Big Bang never happened. The evidence for an expanding universe remains overwhelming, nor does it automatically invalidate decades of cosmological research. But it does suggest that our understanding of how the universe evolved, from its earliest moments to the present day, may still contain missing chapters. The expansion of the cosmos appears to carry a hidden secret, one encoded not in spectacular images or dramatic explosions, but in a handful of numbers that refuse to agree. And sometimes, throughout the history of science, it is precisely those stubborn numbers that lead to the greatest discoveries of all. The discovery of unexpectedly massive galaxies had already shaken astronomers' confidence in the standard timeline of the early universe. The appearance of mature spiral galaxies pushed that discomfort even further. But then the James Webb Space Telescope uncovered something even more astonishing: something that many researchers describe as one of the greatest challenges facing modern cosmology. Hidden within some of the earliest galaxies ever observed were enormous supermassive black holes, objects so massive that, according to our current understanding of physics, they simply should not have had enough time to exist. These were not ordinary black holes left behind by dying stars. They contained millions, and in some cases even billions, of times the mass of our Sun. Even more extraordinary was their age. Some of them were already present less than 500 million years after the Big Bang. It was a discovery that immediately raised an unsettling question. If these black holes really are as massive as they appear, then how did they grow so quickly in such a remarkably short period of cosmic history? To understand why this problem is so profound, we first need to understand how astronomers believe black holes normally grow. Most black holes begin their lives when extremely massive stars exhaust their nuclear fuel. Without the outward pressure generated by fusion, gravity overwhelms the star, causing its core to collapse into an incredibly dense object. If the remaining core contains enough mass, it forms a black hole. These stellar black holes usually weigh somewhere between a few and several dozen times the mass of our Sun. On cosmic scales, they are relatively small. They are the black holes created through ordinary stellar evolution, and thousands of them are thought to exist throughout the Milky Way alone. Growing from one of these stellar black holes into a supermassive black hole, however, is an entirely different challenge. According to conventional theory, the process takes an enormous amount of time. A black hole grows by pulling nearby matter inward. Gas, dust, stars, and occasionally even other black holes fall toward it. But this growth cannot happen infinitely fast. As material spirals into a black hole, it forms a brilliantly glowing accretion disk. Friction within that disk heats the gas to extraordinary temperatures, causing it to emit enormous amounts of radiation. Ironically, that radiation pushes outward against additional infalling matter. The brighter the black hole becomes, the harder it becomes for new material to continue falling inward. This natural balance places a theoretical speed limit on black hole growth, known as the Eddington limit. The Eddington limit is one of the most important concepts in astrophysics. It represents the maximum rate at which a black hole can steadily consume matter before its own radiation begins blowing surrounding gas away. Imagine trying to fill a bucket with water while a powerful fan continuously pushes the water back out. You can certainly keep adding more water, but only up to a certain rate. Beyond that point, the outward force becomes too strong. Black holes face a similar restriction. Even under ideal conditions, growing from a relatively small stellar remnant into a billion solar mass monster should require hundreds of millions, or more commonly, billions, of years of nearly uninterrupted feeding. That timeline seemed perfectly reasonable before the launch of the James Webb Space Telescope. Then Webb began looking toward the earliest galaxies. Among its most remarkable discoveries were brilliant compact objects whose spectra displayed unmistakable signatures of actively feeding black holes. Many belonged to the mysterious class of objects astronomers now call the little red dots. Others resembled young quasars, among the brightest objects anywhere in the universe. Spectroscopic observations revealed broad emission lines produced by gas moving at thousands of kilometers per second under the influence of immense gravity. These were exactly the fingerprints astronomers expect to see around actively accreting supermassive black holes. The conclusion was astonishing. Massive black holes were already present when the universe was less than 500 million years old. Not merely forming, already enormous. This immediately created a mathematical problem. Suppose a black hole begins as the collapsed remnant of a massive star weighing perhaps 100 solar masses. Even if it continuously accreted matter at the maximum rate allowed by the Eddington limit without interruption, a nearly impossible ideal, it would struggle to reach billions of solar masses within such a short cosmic time span. In reality, black holes rarely enjoy perfect feeding conditions. Star formation consumes available gas. Supernova explosions blast material away. Radiation from the black hole itself limits further accretion. Galaxy mergers disturb surrounding matter. Every one of these processes slows growth even further. Yet Webb was showing astronomers black holes that appeared to have ignored those limitations entirely. It was almost as if someone had started reading a novel from the middle. The opening chapters describing their formation seemed to be missing. Naturally, astronomers first questioned the measurements. Perhaps these black holes were smaller than initial estimates suggested. Perhaps surrounding stars contributed more light than expected. Perhaps the objects were not as distant as originally believed. These possibilities had to be investigated carefully. Over the following months, additional spectroscopy confirmed many of the original observations. While individual mass estimates were refined, the broader picture remained remarkably consistent. The early universe truly appeared to host black holes far larger than conventional models predicted. Researchers immediately began searching for explanations. One of the most promising ideas involves something known as direct collapse black holes. Instead of beginning as ordinary stellar remnants, these hypothetical objects may have formed directly from enormous clouds of primordial gas. Under very specific conditions, a gigantic gas cloud might collapse almost entirely under its own gravity without first fragmenting into individual stars. Such a collapse could produce a black hole containing 100,000 or even 1 million solar masses almost immediately. Starting from such a massive seed would dramatically shorten the time required to reach the enormous sizes observed by Webb. The idea is elegant. Unfortunately, it is also extremely difficult. Direct collapse requires very unusual environmental conditions. The gas must remain extraordinarily hot while avoiding fragmentation into stars. Nearby radiation fields must suppress cooling. Turbulence must remain within a narrow range. Whether these conditions occurred frequently enough in the early universe remains one of the most actively debated questions in modern astrophysics. Another possibility focuses on the first generation of stars, the so-called population 3 stars. Because the young universe contained almost no heavy elements, these stars may have grown hundreds of times more massive than those forming today. Their enormous masses could have produced significantly larger black hole seeds after collapse. Instead of beginning with black holes only 10 or 20 times the sun's mass, perhaps nature routinely produced seeds weighing several hundred or even 1,000 solar masses. This certainly helps, but many calculations suggest it still may not be enough. Even starting from these larger seeds, black holes must continue growing at extraordinary rates for hundreds of millions of years with remarkably few interruptions. The timeline remains uncomfortably tight. Some researchers, therefore, considered an even more radical possibility. Perhaps the Eddington limit itself is not always an absolute barrier. Certain theoretical models predict brief episodes of super Eddington accretion, during which black holes consume matter faster than classical theory normally allows. Under specific circumstances, the geometry of the infalling gas may trap some of the outgoing radiation, reducing its ability to halt further accretion. In effect, the black hole may temporarily overheat without immediately blowing away its food supply. If such episodes were common in the early universe, black holes could grow dramatically faster than conventional models predict. Evidence for this process exists in several nearby systems, but whether it can explain Webb's earliest supermassive black holes remains uncertain. Other scientists turned their attention to galaxy mergers. The infant universe was far more crowded than today's cosmos. Galaxies collided frequently, bringing together gas, stars, and central black holes. Repeated mergers could accelerate black hole growth by delivering fresh material directly into galactic centers, while simultaneously combining existing black holes into larger ones. Again, the idea appears promising. Again, the numbers remain challenging. Many simulations suggest that even extremely frequent mergers struggle to reproduce the enormous masses inferred for some of Webb's earliest quasars. This growing collection of explanations highlights something important. No single idea has yet solved the mystery completely. Every proposed solution explains part of the evidence while creating new questions elsewhere. Direct collapse requires rare conditions. Population 3 stars may not produce sufficiently massive seeds. Super Eddington accretion remains difficult to sustain for long periods. Galaxy mergers help, but perhaps not enough. Individually, each mechanism contributes something useful. Together, they may eventually explain the observations. Or perhaps they are still missing one crucial piece of the puzzle. This is precisely why these discoveries have generated so much excitement throughout the astronomical community. For decades, supermassive black holes were considered the products of slow cosmic evolution. Their enormous masses reflected billions of years of steady growth, countless mergers, and an almost unimaginable passage of time. The James Webb Space Telescope has challenged that comfortable assumption. Instead of patiently waiting billions of years, the universe appears to have been building gigantic black holes almost immediately after the first galaxies emerged. Perhaps the early universe was far more efficient than we ever imagined. Perhaps entirely new physical processes operated during cosmic dawn. Or perhaps these ancient giants are quietly pointing toward gaps in our understanding of gravity, galaxy formation, or even the fundamental history of the universe itself. Whatever the final explanation proves to be, one conclusion has already become impossible to ignore. The James Webb Space Telescope was expected to show astronomers the universe exactly as their theories predicted. Instead, it has revealed black holes that seem to have outrun time itself. Cosmic monsters that, according to everything we thought we understood, should never have had the chance to exist. The earliest universe was, in many ways, astonishingly simple. If you could somehow travel back nearly 13.8 billion years to the moments immediately following the Big Bang, you would not find planets, rocky worlds, oxygen-rich atmospheres, or the complex chemistry that makes life possible today. Instead, you would encounter an immense ocean of almost pure hydrogen and helium stretching across an expanding cosmos. These two light elements dominated everything. Hydrogen accounted for roughly 3/4 of ordinary matter, while helium made up most of the rest. Only tiny traces of lithium and a handful of other light elements existed. Everything heavier than that, the carbon in our bodies, the oxygen we breathe, the iron in our blood, the calcium in our bones, the silicon inside computers, and the gold in jewelry, simply did not exist yet. The universe had not had enough time to manufacture them. According to modern astrophysics, these heavier elements, collectively known as metals, are created deep inside the cores of stars through nuclear fusion. Every atom heavier than helium is the product of stellar evolution, forged over immense spans of time and scattered across space through violent supernova explosions. This process is one of the fundamental building blocks of cosmic evolution. Yet once again, the James Webb Space Telescope has revealed evidence suggesting that this timeline may not be as straightforward as scientists once believed. Astronomers use the word metallicity in a way that differs from everyday language. Outside astronomy, metals refer to familiar materials like iron, copper, aluminum, or gold. In astronomy, however, every element heavier than hydrogen and helium is classified as a metal. Oxygen is a metal. Carbon is a metal. Nitrogen is a metal. Silicon, magnesium, neon, sulfur, calcium, and iron all belong to the same category. This simple definition allows astronomers to estimate how many generations of stars have contributed to the evolution of a galaxy. A galaxy composed almost entirely of hydrogen and helium is considered chemically primitive. A galaxy rich in heavier elements has clearly undergone extensive stellar evolution, because only repeated generations of stars can gradually enrich interstellar gas with these newly forged atoms. The process begins inside the first stars. When gravity compresses enormous clouds of hydrogen gas, temperatures rise until nuclear fusion ignites. Hydrogen atoms fuse together to create helium, releasing extraordinary amounts of energy. In more massive stars, fusion continues beyond helium, gradually producing carbon, oxygen, neon, magnesium, silicon, sulfur, and eventually iron. Iron marks an important boundary because fusing elements heavier than iron consumes energy rather than producing it. Once an enormous star develops an iron core, fusion can no longer support its weight. Gravity takes over, the core collapses, and the star explodes as a supernova. These spectacular explosions scatter newly created heavy elements across surrounding space, enriching nearby gas clouds that later collapse to form new generations of stars. This cycle repeats again and again over cosmic history. Each generation of stars leaves behind more heavy elements than the one before. Gradually, galaxies become chemically richer. Astronomers have relied upon this principle for decades. Metallicity functions almost like a cosmic clock. A galaxy with very low metallicity is expected to be extremely young because relatively few stars have lived and died. A galaxy with high metallicity must have experienced multiple generations of stellar evolution. The relationship is not perfect, but has become one of the most valuable tools for reconstructing the history of galaxies throughout the universe. Before the James Webb Space Telescope launched, cosmological models made a clear prediction. The earliest galaxies should possess very low metallicities. They existed only a few 100 million years after the Big Bang, leaving little time for repeated cycles of star formation and supernova explosions. Their stars should still consist largely of primordial hydrogen and helium, with only modest traces of heavier elements. Webb was expected to confirm this picture with unprecedented precision. Instead, it revealed another surprise. Spectroscopic observations of several ancient galaxies suggested chemical compositions richer than expected. Using its extraordinarily sensitive infrared instruments, Webb separated the light emitted by distant galaxies into detailed spectra, allowing astronomers to identify the fingerprints of individual chemical elements. Certain galaxies displayed unexpectedly strong signatures of oxygen, carbon, nitrogen, and other heavy elements. Although not every early galaxy exhibited these properties, enough examples appeared to attract serious attention throughout the astronomical community. The implications were immediately obvious. If these measurements were correct, then some galaxies had already experienced multiple generations of stellar evolution only a few 100 million years after the Big Bang. That timeline appeared astonishingly compressed. Stars do not produce heavy elements instantly. Massive stars certainly evolve much faster than stars like our Sun, often living only a few million years before exploding. But creating significant metallicity across an entire galaxy requires not just one generation of stars, but repeated cycles of star formation, stellar evolution, supernova explosions, gas mixing, and subsequent generations of new stars. Every stage consumes valuable cosmic time. According to many simulations, there simply should not have been enough time available. Naturally, astronomers first questioned the observations themselves. Perhaps dust inside these distant galaxies altered their spectra. Perhaps emission lines from different elements overlapped in unexpected ways. Maybe the galaxies contained unusually active black holes whose radiation complicated chemical measurements. Perhaps the metallicities had simply been overestimated because existing models failed to describe conditions in the earliest galaxies accurately. These possibilities had to be examined carefully. As additional observations accumulated, the picture became increasingly nuanced. Some early measurements were revised as more detailed spectroscopy became available. In several cases, metallicities proved somewhat lower than originally estimated. Yet the broader mystery remained. A number of galaxies continued displaying levels of chemical enrichment surprisingly difficult to reconcile with conventional timelines of galaxy evolution. One possible explanation focuses on the very first generation of stars, known as population 3 stars. These hypothetical primordial stars may have been unlike almost anything visible in today's universe. Because the young cosmos contained almost no heavy elements, gas clouds cooled differently, potentially allowing stars to grow to extraordinary masses. Some theoretical models suggest population 3 stars may have reached hundreds of times the mass of the Sun. Such enormous stars would live extremely short lives, perhaps only 2 or 3 million years, before exploding in incredibly energetic supernovae capable of enriching surrounding gas remarkably quickly. If the early universe produced large numbers of these gigantic stars, chemical evolution may have progressed much faster than previously believed. This idea remains one of the leading explanations, but it is not without challenges. No population 3 star has ever been observed directly. Their existence is strongly supported by theoretical models, yet astronomers still lack definitive observational confirmation. Moreover, reproducing Webb's highest metallicity estimates often requires extraordinarily efficient star formation occurring across multiple generations in surprisingly little time. Another possibility concerns the efficiency with which early galaxies recycled their gas. Modern galaxies frequently lose significant amounts of material through stellar winds, supernova explosions, and energetic outflows driven by central black holes. If primordial galaxies retained a much larger fraction of their enriched gas, heavy elements could accumulate far more rapidly than current simulations predict. Successive generations of stars would form from increasingly metal-rich material, accelerating chemical evolution throughout the galaxy. Others have suggested that our simulations of early galaxy formation simply underestimate how violently the first billion years unfolded. The infant universe may have experienced bursts of star formation unlike anything commonly observed today. Instead of gradually producing stars over billions of years, primordial galaxies may have converted enormous reservoirs of gas into massive stars with astonishing efficiency. Repeated supernova explosions would then enrich surrounding material almost continuously, dramatically compressing the timeline required to produce significant metallicity. Again, this explanation appears plausible. Again, it raises new questions. If star formation proceeded this efficiently, why do some observations continue matching conventional models while others appear dramatically different? Why are certain galaxies surprisingly enriched while others remain chemically primitive? What determines these different evolutionary paths? These questions remain unanswered. The metallicity mystery becomes even more intriguing when considered alongside Webb's other discoveries. Unexpectedly massive galaxies. Mature spiral structures appearing far earlier than expected. Supermassive black holes growing with astonishing speed. The mysterious little red dots. Individually, each anomaly might eventually find a conventional explanation. Collectively, however, they suggest that the first billion years of cosmic history may have been a period of astonishing complexity, far more dynamic than the relatively smooth evolutionary picture astronomers had imagined before Webb began observing the distant universe. Importantly, none of this means that the Big Bang itself has been disproven. The production of hydrogen and helium during the universe's earliest minutes remains one of the strongest successes of modern cosmology. Webb has not challenged those fundamental predictions. Instead, it is forcing scientists to reconsider what happened after the first stars ignited. Perhaps stellar evolution progressed with extraordinary speed. Perhaps the first galaxies formed under physical conditions unlike anything present today. Or perhaps entirely new processes influenced chemical evolution during the universe's infancy. Whatever the ultimate explanation proves to be, the metallicity mystery carries an important message. The early universe was not merely a simpler version of today's cosmos. It may have been a fundamentally different environment, operating under conditions that allowed galaxies, stars, black holes, and chemical elements to evolve with breathtaking efficiency. Every spectrum captured by the James Webb Space Telescope represents light that has traveled across more than 13 billion years of expanding space. Hidden within that ancient light are the fingerprints of atoms forged inside the very first stars. Those fingerprints are telling astronomers a story they did not expect to hear. a story in which the universe appears to have grown older, richer, and more chemically complex far sooner than anyone had imagined. The James Webb Space Telescope had already delivered one surprise after another. It revealed galaxies that appeared far more massive than expected. It uncovered supermassive black holes that seemed to have grown impossibly fast. It detected unexpectedly high metallicity in some of the earliest galaxies, suggesting multiple generations of stars had already lived and died within a remarkably short period of cosmic history. Many astronomers hoped these discoveries might eventually fit together within refined models of galaxy formation. But then Webb uncovered yet another puzzle, one that challenged an entirely different part of our understanding of cosmic evolution. Among the countless distant galaxies captured by its powerful infrared instruments were objects that appeared to have already reached the end of their lives. They were no longer actively forming stars. Their brightest stellar nurseries had gone dark. Instead of glowing with the blue light of young, hot stars, they were dominated by older, redder stellar populations. In modern astronomy, these objects are often described as red and dead galaxies. The phrase may sound dramatic, but reflects a very real stage in galactic evolution. The mystery was not that these galaxies existed. The mystery was when they existed. According to Webb's observations, some of them had already entered this mature phase only about 1 billion years after the Big Bang, a stage that many traditional models suggested should require many billions of years to achieve. To appreciate why this discovery is so remarkable, it helps to understand how galaxies normally evolve. Galaxies are not static collections of stars. They're dynamic systems that constantly change over cosmic time. In their youth, galaxies are rich in cold hydrogen gas, the essential fuel for star formation. Gravity causes enormous clouds of this gas to collapse, giving birth to countless new stars. Massive young stars shine with an intense blue light, making actively star-forming galaxies appear bright and vibrant. These stellar nurseries are often chaotic environments filled with glowing nebulae, powerful stellar winds, and frequent supernova explosions. Astronomers refer to this stage as an era of vigorous star formation, and many young galaxies spend billions of years continuously converting gas into new generations of stars. Eventually, however, this activity begins to slow. Some galaxies gradually consume most of their available gas. Others lose gas through powerful outflows driven by exploding stars or actively feeding supermassive black holes. Galaxy mergers can also disrupt the supply of cold gas, while energetic radiation from central black holes may heat surrounding materials so intensely that it can no longer collapse to form new stars. Whatever the cause, once a galaxy loses access to sufficient cold gas, star formation begins to fade. Without newborn blue stars continually replacing older generations, the galaxy's appearance slowly changes. Short-lived blue stars die first, leaving behind longer-lived red stars that dominate the galaxy's light. Over billions of years, the entire system transforms into what astronomers call a quiescent galaxy, a galaxy where little or no significant star formation remains. This transition has long been considered one of the final chapters of galaxy evolution. In a nearby universe, many of the largest elliptical galaxies belong to this category. They contain enormous populations of ancient stars, but produce relatively few new ones. Their brightest periods of growth ended billions of years ago. Because reaching this stage requires exhausting or removing vast reservoirs of gas, astronomers believed it was a slow process unfolding over much of cosmic history. Before Webb launched, computer simulations reflected exactly this expectation. The earliest galaxies should be energetic, blue, and actively forming stars. Only after many billions of years would enough gas be consumed or expelled for galaxies to become fully quiescent. According to this picture, finding numerous red and dead galaxies in the very early universe should have been extremely unlikely. Yet once again, Webb showed something unexpected. Using its extraordinary infrared sensitivity, The telescope observed galaxies whose light had traveled for more than 12 billion years before reaching Earth. Many belonged to an era when the universe itself was less than 1 billion years old. Surprisingly, several of these distant systems displayed spectral signatures indicating that active star formation had already slowed dramatically, or in some cases, nearly stopped altogether. Their stellar populations appeared surprisingly old. Instead of being dominated by brilliant young stars, they seemed filled with mature stars that had formed much earlier. For astronomers, this was deeply puzzling. If these galaxies had already stopped forming stars by the time Webb observed them, then their major episodes of star formation must have occurred even earlier. In other words, they would have needed to form enormous numbers of stars at extraordinary speed shortly after the Big Bang, and then somehow shut the entire process down within only a few 100 million years. That timeline seemed almost impossibly compressed. To illustrate the challenge, imagine constructing a vast city in only a few months and then immediately abandoning all new construction forever. Roads, buildings, bridges, power stations, and neighborhoods would all need to appear almost simultaneously before development suddenly ceased. The universe appeared to have done something similar. These galaxies seemed to have completed most of their stellar growth before cosmological models expected the process to have properly begun. Naturally, astronomers first questioned the observations. Could dust inside these galaxies make young stellar populations appear older than they really were? Could active galactic nuclei powered by supermassive black holes alter the observed colors? Were the distances incorrect? Perhaps these galaxies were closer than initially estimated, making them older than they appeared. As with every major Webb discovery, researchers carefully reanalyzed the data using multiple independent techniques. Spectroscopy became especially important because it allowed astronomers to identify the chemical fingerprints and ages of stellar populations far more accurately than images alone. While individual galaxies remained subject of active debate, the overall evidence increasingly suggested that genuinely quiescent galaxies did exist surprisingly early in cosmic history. This forced researchers to confront an entirely new question. How does a galaxy stop forming stars so quickly? Several possible explanations emerged. One idea focuses on supermassive black holes. Although black holes are famous for consuming matter, they also release enormous amounts of energy as gas falls toward them. This process, known as active galactic nucleus feedback, can generate intense radiation, powerful particle jets, and high-speed winds capable of heating or ejecting cold gas from an entire galaxy. Without cold gas, star formation rapidly declines. If the earliest supermassive black holes grew faster than previously believed, as Webb's other discoveries already suggest, they may also have shut down star formation much earlier than expected. Another possibility involves extremely efficient bursts of star formation. Rather than slowly producing stars over billions of years, some primordial galaxies may have converted nearly all of their available gas into stars within a remarkably short period. Once the gas supply was exhausted, star formation naturally came to an end. In this scenario, galaxies did not need to lose their gas. They simply used it up far faster than conventional simulations predicted. Galaxy mergers provide another potential explanation. Frequent collisions between young galaxies can trigger enormous bursts of star formation while simultaneously feeding central black holes. The combined effects of rapid star formation and energetic black hole activity may quickly consume and expel the remaining gas, leaving behind a quiescent galaxy much sooner than expected. Some theorists have suggested that current simulations underestimate the complexity of the first billion years after the Big Bang. Conditions during cosmic dawn may have been fundamentally different from those found in later epochs. Higher gas densities, more frequent interactions, and unusually massive first-generation stars could all accelerate galaxy evolution beyond what existing models currently reproduce. Yet every explanation introduces new challenges. If galaxies formed stars this efficiently, why do many other early galaxies remain actively forming stars? If black holes shut down star formation so effectively, how did they themselves grow to enormous masses without exhausting their own fuel supply? If mergers were responsible, why do some quiescent galaxies appear surprisingly undisturbed? Each answer seems to generate another question. This is becoming a familiar pattern throughout the James Webb mission. Unexpectedly massive galaxies, ancient spiral structures, little red dots, rapidly growing supermassive black holes, high metallicity, and now galaxies that already appear old before the universe itself has reached its first billion years. Individually, each discovery can perhaps be accommodated through refinements to existing theories. Together, however, they paint a picture of an early universe evolving with astonishing speed. Instead of a slow, gradual process unfolding over billions of years, Webb is revealing episodes of intense activity compressed into remarkably short periods of cosmic history. Galaxies appear to build stars faster, enrich themselves chemically sooner, organize into stable structures earlier, grow black holes more rapidly, and in some cases, stop forming stars altogether long before astronomers expected. Importantly, none of this means the Big Bang has been disproven. The evidence for an expanding universe, the cosmic microwave background, and Big Bang nucleosynthesis remains extraordinarily strong. What Webb is challenging is not necessarily how the universe began, but how quickly it grew up. The first billion years after the Big Bang may have been far more dynamic, violent, and efficient than decades of theoretical models predicted. Perhaps these red and dead galaxies are simply rare exceptions, representing unusual environments where galaxy evolution proceeded at breathtaking speed. Or perhaps they're early clues that our understanding of galaxy formation is still incomplete. Whatever the ultimate explanation proves to be, one thing has become increasingly clear. The James Webb Space Telescope has transformed the first billion years of cosmic history from one of the most predictable chapters in astronomy into one of its greatest mysteries. Instead of finding youthful galaxies just beginning their journey, Webb has revealed ancient-looking systems that seem to have lived entire cosmic lifetimes before the universe itself had barely reached its infancy. The discovery of surprisingly mature galaxies, impossibly massive black holes, and unexpected chemical complexity has forced astronomers to reconsider many details of the early universe. Yet one of the oldest and most mysterious challenges to modern cosmology was discovered long before the James Webb Space Telescope ever left Earth. It is not hidden inside distant galaxies or ancient quasars. Instead, it is written across the oldest light in the entire universe, the faint afterglow of the Big Bang itself. This ancient radiation, known as the cosmic microwave background, has been one of the strongest pillars supporting the Big Bang model for more than half a century. It is often described as the universe's baby picture, a snapshot of the cosmos when it was only about 380,000 years old. According to standard cosmology, this radiation should appear almost perfectly random, with tiny fluctuations scattered evenly across the sky. There should be no preferred direction, no hidden pattern, and certainly no enormous cosmic alignment stretching across billions of light years. Yet when scientists began studying this ancient light in extraordinary detail, they found something deeply unexpected. Certain large-scale temperature fluctuations appeared to line up along a single mysterious direction. The alignment was so strange that researchers jokingly gave it a name borrowed from politics and history. They called it the axis of evil. The nickname was meant to be humorous, but the scientific puzzle behind it remains one of the most controversial mysteries in cosmology. To understand why this discovery matters, we first need to understand what the cosmic microwave background actually is. Nearly 14 billion years ago, shortly after the Big Bang, the universe was unimaginably hot and dense. Temperatures were so extreme that electrons could not remain attached to atomic nuclei. Instead, the universe existed as a glowing plasma filled with free electrons, protons, helium nuclei, and intense radiation. Photons, the particles of light, could not travel freely because they constantly collided with these charged particles. The young universe resembled the interior of a dense fog where light scattered in every direction without ever escaping. As the universe expanded, however, everything gradually cooled. Roughly 380,000 years after the Big Bang, temperatures finally dropped enough for electrons to combine with atomic nuclei, forming the first neutral atoms. Suddenly, the constant scattering stopped. For the first time in cosmic history, light was free to travel enormous distances without being trapped by the surrounding plasma. That ancient light has been crossing the universe ever since. During its nearly 14 billion-year journey, the expansion of space stretched its wavelength from visible light into the microwave region of the electromagnetic spectrum. Today, astronomers detect it as an almost perfectly uniform glow surrounding the entire sky. Every direction we look contains this ancient radiation. It is the oldest light humanity has ever observed. The cosmic microwave background became one of the greatest triumphs of modern cosmology because it confirmed several remarkable predictions of the Big Bang theory. Measurements made by satellites, such as COBE, WMAP, and later Planck revealed that the background radiation has nearly the same temperature everywhere, differing by only tiny fractions of a degree. These minute temperature variations represent the primordial density fluctuations from which all future galaxies, stars, and planets eventually formed. Without them, gravity would have had no seed from which cosmic structure could grow. One of the fundamental assumptions behind this picture is known as the cosmological principle. It is an elegantly simple idea. On sufficiently large scales, the universe should be homogeneous and isotropic. Homogeneous means matter is distributed uniformly throughout the cosmos when viewed over enormous distances. Isotropic means the universe should look essentially the same in every direction. There should be no special location and no preferred cosmic orientation. Whether you observe the sky toward one constellation or another, the statistical properties of the universe should remain the same. This assumption lies at the heart of nearly every modern cosmological model. For decades, observations appear to support it remarkably well. Then scientists began analyzing the cosmic microwave background with increasing precision. Instead of examining only its average temperature, researchers carefully studied the tiny fluctuations scattered across the sky. These temperature variations can be decomposed mathematically into different angular scales, almost like separating the notes within a complex piece of music. Most of these fluctuations behaved exactly as expected. They appeared random, matching predictions from the standard cosmological model with extraordinary accuracy. But the largest scale fluctuations told a different story. Several independent analyses suggested that two of the strongest patterns, the quadrupole and the octupole, appeared unexpectedly aligned with one another. Rather than pointing in random directions as theory predicted, they seemed to define a common cosmic axis. This was astonishing. Random patterns are not supposed to organize themselves this way. The probability of such an alignment occurring purely by chance appeared surprisingly low, although estimates varied, depending on the statistical methods used. Because the discovery challenged one of cosmology's most cherished assumptions, researchers gave the anomaly an intentionally provocative nickname, the axis of evil. The name quickly attracted attention far beyond the scientific community. Some interpreted it as evidence that the universe possesses a preferred direction, something Einstein's cosmological framework never anticipated. Others speculated about entirely new physics operating on the largest observable scales. More sensational claims even suggested the anomaly hinted that our universe might not be fundamentally random at all. Professional astronomers, however, responded much more cautiously. Extraordinary claims require extraordinary evidence. The first question researchers asked was whether the alignment might simply result from contamination inside our own galaxy. The Milky Way emits microwave radiation that can interfere with measurements of the cosmic microwave background. Dust clouds, magnetic fields, and energetic particles all contribute unwanted signals that must be carefully removed before cosmologists analyze the ancient radiation itself. If even a small amount of foreground contamination remained, it could potentially create artificial large-scale patterns. Teams working on both the WMAP and Planck missions devoted enormous effort to eliminating these effects. Sophisticated cleaning algorithms separated galactic emission from the primordial microwave background using observations across multiple frequencies. While these corrections improve the data considerably, the mysterious alignment stubbornly refused to disappear completely. Another possibility involved statistical coincidence. The universe contains an enormous number of measurable properties. Whenever scientists examine vast data sets, unusual patterns occasionally emerge purely by chance. Some cosmologists argue that the axis of evil represents exactly this kind of statistical fluke. According to this view, because researchers have examined countless possible alignments and anomalies, it is unsurprising that one particularly unusual pattern eventually appeared. In other words, perhaps the axis of evil only seems remarkable because human beings naturally notice unexpected coincidences. Others disagree. Several independent studies have argued that the alignment remains statistically significant even after accounting for these selection effects. Although estimates differ, many researchers conclude that the anomaly deserves serious attention rather than casual dismissal. If the alignment is genuinely real, its implications could be profound. A preferred direction in the universe would challenge one of the central assumptions underlying the standard cosmological model. The universe would no longer appear perfectly isotropic on the largest observable scales. Such a discovery would require astronomers to reconsider how cosmic inflation unfolded shortly after the Big Bang. Inflation is believed to have stretched tiny quantum fluctuations into the seeds of all future cosmic structure, while simultaneously smoothing the universe into remarkable uniformity. An unexpected large-scale alignment might indicate that inflation behaved differently than existing models predict, or perhaps that entirely new physical processes influenced the earliest moments of cosmic history. Over the years, theorists have proposed numerous explanations. Some suggest the anomaly reflects subtle effects produced by the overall shape or topology of the universe. If space itself possesses a more complicated geometry than currently assumed, large-scale alignments might naturally emerge. Others explore the possibility of previously unknown interactions involving dark energy or dark matter. A few researchers have even considered whether the observable universe may retain faint imprints from conditions existing before cosmic inflation began. These ideas remain highly speculative. At present, no explanation has achieved widespread acceptance. Interestingly, the axis of evil becomes even more intriguing when viewed alongside the growing collection of puzzles emerging from the James Webb Space Telescope. Unexpectedly massive galaxies, ancient spiral structures, rapidly growing supermassive black holes, high metallicity, quiescent galaxies appearing astonishingly early. None of these discoveries directly prove that the axis of evil reflects new physics. Yet together, they illustrate a broader pattern. Modern cosmology continues achieving extraordinary successes while simultaneously encountering persistent anomalies that refuse to disappear. Importantly, the axis of evil does not disprove the Big Bang. The cosmic microwave background remains one of the strongest pieces of evidence that the universe evolved from an extremely hot and dense early state. The anomaly affects the statistical distribution of temperature fluctuations, not the existence of the background radiation itself. Most cosmologists continue to regard the Big Bang as overwhelmingly supported by observational evidence. What the axis of evil does challenge is something more subtle. It asks whether the universe is truly as simple, as uniform, and as directionless as we have long assumed. Perhaps the mysterious alignment will eventually prove to be nothing more than an extraordinarily unlikely coincidence. Perhaps future observations will reveal hidden systematic effects that fully explain it. Or perhaps it represents one of those rare anomalies that quietly signal the beginning of an entirely new chapter in physics. History reminds us that some of science's greatest breakthroughs began not with dramatic discoveries, but with small inconsistencies hiding inside otherwise successful theories. The orbit of Mercury hinted at general relativity. Tiny irregularities in atomic spectra gave birth to quantum mechanics. And today, the oldest light in the universe contains a faint, enigmatic alignment that continues to resist simple explanation. Whether it ultimately proves to be a statistical curiosity or evidence of something profoundly new, the axis of evil serves as another reminder that the universe still guards secrets even in the light that has been traveling toward us since the dawn of time. The deeper astronomers look into the universe, the more they discover that galaxies are not scattered randomly through space. Instead, they form an enormous cosmic web, a vast network of filaments, clusters, and superclusters connected across unimaginable distances. Between these glowing strands lie immense cosmic voids, regions so empty that millions of light-years can pass without encountering a single major galaxy. This large-scale structure is one of the greatest triumphs of modern cosmology. Computer simulations based on the Big Bang, dark matter, and gravity reproduce the cosmic web with remarkable accuracy. Tiny density fluctuations present shortly after the Big Bang gradually grew under the influence of gravity, eventually forming the galaxies, clusters, and filaments we observe today. It is an elegant picture that has successfully explained much of the universe's large-scale architecture. Yet once again, hidden within the observations is a mystery that refuses to fit comfortably inside that framework. Scattered across billions of light-years are structures so enormous that many cosmologists struggle to explain how they could have formed at all. Among them, none has attracted more attention than the Hercules, Corona Borealis Great Wall, a colossal arrangement of galaxies and galaxy clusters stretching across an estimated 10 billion light-years. Its sheer size raises an uncomfortable question. If the universe began in a nearly smooth and uniform state, how could something this unimaginably large ever have formed? To appreciate why this discovery is so surprising, it helps to understand what cosmologists expected to find. According to the Standard Model, the early universe was remarkably uniform. Measurements of the cosmic microwave background show temperature variations of only about 1 part in 100,000. Those tiny fluctuations represented slightly denser regions where gravity would eventually begin gathering matter. Over billions of years, these regions grew into galaxies, galaxy clusters, and the vast interconnected filaments that make up today's cosmic web. However, there is an important limitation. Gravity works slowly across enormous distances. While it can gradually build structures over hundreds of millions or even billions of years, there's a practical upper limit to how large coherent structures should become within the age of the observable universe. This expectation is known as the cosmological principle, the assumption that on sufficiently large scales the universe should appear statistically homogeneous. In simpler terms, although galaxies form clusters and superclusters locally, the universe should become increasingly smooth when viewed across immense distances. Individual structures may certainly be enormous, but beyond a certain scale, they should blend into an overall uniform distribution. Most cosmological models predict that coherent structures larger than roughly 1 to 2 billion light-years should become increasingly rare and eventually impossible. The reason is straightforward. The universe simply has not existed long enough for gravity to organize matter across distances vastly exceeding that scale. For decades, observations appeared broadly consistent with this picture. Astronomers mapped countless galaxy clusters and identified spectacular structures, such as the Sloan Great Wall and the CFA-2 Great Wall. These immense formations already stretched hundreds of millions of light-years across, demonstrating that gravity is capable of creating truly gigantic patterns. Although impressive, They remained within the general expectations of cosmological simulations. Then came a discovery that seemed to redefine the meaning of large. In 2013, astronomers studying gamma-ray bursts noticed something unexpected. Gamma-ray bursts are among the most energetic explosions in the universe, produced during catastrophic events such as the collapse of massive stars or the merger of neutron stars. Because they can be observed across enormous distances, they serve as valuable markers for mapping the distribution of matter in the distant universe. As researchers plotted the locations of these explosions, they found an unusual concentration within a particular region of the sky, corresponding to the constellations Hercules and Corona Borealis. The clustering was extraordinary. Instead of appearing randomly scattered, the gamma-ray bursts seemed to trace an immense cosmic structure stretching across an estimated 10 billion light-years. To put that into perspective, the observable universe itself measures roughly 93 billion light-years in diameter. The Hercules, Corona Borealis Great Wall, would therefore span more than 1/10 of the entire observable cosmos. If the estimates are correct, it would be the largest known structure ever identified. The implications were immediately controversial. How could gravity possibly organize matter across such an extraordinary distance? According to conventional models, structures of this scale should never have had enough time to form since the Big Bang. Naturally, astronomers approached the claim with caution. Extraordinary discoveries demand extraordinary evidence. The first question concerned the observations themselves. Unlike ordinary galaxy surveys, the Hercules, Corona Borealis Great Wall, was identified primarily through the distribution of gamma-ray bursts rather than direct images of galaxies. Gamma-ray bursts are relatively rare events, meaning the available dataset is much smaller than traditional galaxy catalogs. Some researchers argued that random statistical fluctuations might create the illusion of a giant structure where none actually exists. This possibility remains an active area of debate. Several independent analyses have suggested that the apparent clustering may indeed be statistically significant, while others caution that selection effects and limited sample sizes make definitive conclusions difficult. Unlike nearby galaxy surveys containing millions of objects, gamma-ray burst observations remain comparatively sparse. As additional observations accumulate over the coming years, astronomers hope to determine whether the structure is truly as enormous as current estimates suggest. Even if the Hercules, Corona Borealis Great Wall ultimately proves somewhat smaller than initially reported, it is far from the only unusually large structure challenging cosmologists. The Sloan Great Wall, the huge large quasar group, the giant arc, and several other enormous formations have all sparked similar discussions about the maximum scale of cosmic structure. Individually, each discovery may fit within the statistical limits of current models. Collectively, however, they raise an important question. Has the universe produced more giant structures than our simulations predict? If so, why? One possibility is that current cosmological simulations underestimate the role of dark matter during the universe's early evolution. Dark matter provides the invisible gravitational scaffolding upon which galaxies form. If dark matter clustered more efficiently than expected under certain conditions, enormous structures might emerge more readily than existing models suggest. Another explanation focuses on cosmic inflation. According to the standard theory, the universe underwent an extraordinarily rapid expansion during its earliest fraction of a second. This inflation stretched tiny quantum fluctuations across immense distances, creating the seeds from which all later structure developed. If inflation produced subtle variations larger than current models predict, it might naturally generate unusually massive structures billions of years later. Some theorists have proposed modifications involving dark energy, the mysterious force driving the accelerated expansion of the universe. Because dark energy influences how cosmic structures evolve over billions of years, even slight differences in its behavior could affect the growth of the largest formations. Others argue that no new physics is required at all. The universe is extraordinarily vast. Given enough volume, extremely rare structures may eventually appear purely through chance. Just as flipping a coin thousands of times occasionally produces an unexpectedly long sequence of heads, perhaps the observable universe simply contains a few exceptionally large structures that lie near the extreme edge of statistical expectations. This remains one of the most conservative interpretations, yet not everyone finds it fully satisfying. The Hercules, Corona Borealis Great Wall, becomes particularly intriguing when viewed alongside the growing collection of other cosmological puzzles. The Hubble Tension suggests the universe may be expanding differently than expected. The axis of evil hints at unexpected large-scale alignments in the cosmic microwave background. The James Webb Space Telescope continues revealing galaxies, black holes, and chemical evolution proceeding far faster than theoretical models predicted. None of these anomalies necessarily prove that modern cosmology is fundamentally incorrect. But together, they paint a picture of a universe that appears more complicated than the elegant simplicity envisioned only a decade ago. It is important to emphasize that discoveries like the Hercules, Corona Borealis Great Wall do not invalidate the Big Bang. The overwhelming evidence for an expanding universe, the cosmic microwave background, and Big Bang nucleosynthesis remains exceptionally strong. Instead, these enormous structures challenge the details of how matter organized itself after the Big Bang. They ask whether gravity, dark matter, cosmic inflation, or perhaps entirely unknown physical processes shaped the universe in ways our current simulations have yet to capture. History has shown that astronomy advances whenever observations force theorists to confront unexpected realities. Every new generation of telescopes has revealed phenomena once considered impossible. Pulsars, quasars, dark energy, gravitational waves, and supermassive black holes all transformed our understanding of the cosmos after surprising earlier generations of scientists. Today, giant cosmic structures may represent another chapter in that tradition. Whether the Hercules Corona Borealis Great Wall ultimately proves to be the largest structure in the universe, a rare statistical fluctuation, or evidence that our cosmological models require important revisions, its existence reminds us of something profoundly important. The universe continues to exceed our imagination. Every map we create reveals patterns larger than we expected, structures more intricate than our theories predicted, and mysteries that challenge even our most successful scientific ideas. What once appeared to be a smooth and orderly cosmos now reveals itself as an astonishing tapestry woven across billions of light years, a tapestry whose full story humanity is only beginning to understand. For decades, astronomers dreamed of building a telescope powerful enough to look farther into the universe than ever before. The Hubble Space Telescope had already transformed our understanding of the cosmos, producing breathtaking images that revealed thousands of distant galaxies packed into tiny regions of seemingly empty sky. Those famous deep-field photographs fundamentally changed humanity's perspective. What appeared to be darkness was actually filled with countless galaxies stretching across billions of light years and billions of years of cosmic history. Yet Hubble had its limits. Although revolutionary, it could only peer so far into the early universe. Much of the light from the first galaxies had been stretched by the expansion of space beyond Hubble's most sensitive wavelengths. Astronomers believed that the James Webb Space Telescope would finally overcome this limitation. Equipped with a mirror more than 6 times larger than Hubble's and designed specifically to observe infrared light, Webb promised to reveal the universe's earliest galaxies in unprecedented detail. Most scientists expected its first deep-field image to confirm what decades of cosmological models had predicted. They believed they would see small, primitive galaxies just beginning to assemble a few 100 million years after the Big Bang. Instead, the very first image delivered by the telescope immediately raised questions that continue to echo throughout modern astronomy. When NASA released Webb's first deep field in July 2022, the image quickly became one of the most celebrated astronomical photographs ever taken. Officially centered in the galaxy cluster SMACS 0723, The observation covered only an area of sky roughly equivalent to a grain of sand held at arm's length. Despite observing such a tiny region, the telescope captured thousands of galaxies scattered across nearly every visible part of the image. Some appeared relatively nearby, while countless others lay so far away that their light had been traveling toward Earth for more than 13 billion years. Massive foreground galaxies bent the light of even more distant objects through gravitational lensing, creating spectacular arcs and distorted images predicted by Einstein's theory of general relativity. The picture was visually stunning, but for astronomers, the beauty of the image quickly gave way to something even more important: the scientific data hidden inside it. Almost immediately, researchers began identifying candidate galaxies that appear to exist astonishingly early in cosmic history. Many of these objects seemed significantly brighter, larger, and more numerous than theoretical models had anticipated. Before Webb's launch, simulations predicted that galaxies within the first few hundred million years after the Big Bang would be extremely rare and relatively small. The earliest stars would only recently have begun illuminating the cosmos, and galaxy formation was expected to proceed gradually as gravity slowly assembled matter into increasingly larger structures. Webb appeared to be telling a different story. Instead of finding only a handful of tiny, primitive galaxies, astronomers found entire populations of surprisingly luminous objects scattered throughout the deep field. Some candidate galaxies appeared massive enough to rival systems thought to require far longer to assemble. Others displayed evidence of surprisingly organized structures. Several seemed to contain enough stars that their inferred masses challenged existing simulations of early galaxy formation. The universe, it seemed, had become remarkably busy far sooner than expected. The scientific community reacted with a mixture of excitement and caution. Whenever a new telescope opens an entirely unexplored window on the universe, surprising discoveries are almost guaranteed. Astronomers therefore resisted drawing immediate conclusions. Many of the earliest distance estimates relied on photometric observations, in which a galaxy's brightness is measured through different filters to estimate its redshift, the stretching of its light caused by the expansion of the universe. While highly effective, this technique can occasionally mistake near dusty galaxies for much more distant objects. Spectroscopic observations would be needed to confirm the true distances of these extraordinary candidates. Over the following months, Webb delivered exactly those observations. Some of the most dramatic early claims were revised. A few candidate galaxies turned out to be somewhat closer than initially believed. Others proved less massive after more detailed analysis. This was entirely expected. Scientific progress depends upon testing and refining initial discoveries rather than accepting them unquestioningly. Yet something important remained. Even after these revisions, Webb continued revealing galaxies that appeared surprisingly abundant, surprisingly luminous, and surprisingly mature during the universe's first few 100 million years. While not every headline survived closer examination, the overall pattern refused to disappear. Researchers soon realized that the first deep field had provided only the beginning. As additional observing programs targeted other regions of the sky, the same general picture emerged repeatedly. Ancient galaxies appeared more common than many cosmological simulations predicted. Several possessed unexpectedly high stellar masses. Others showed evidence of chemical enrichment, organized disk-like structures, or rapidly growing supermassive black holes. Instead of representing an isolated curiosity, the first deep field seemed to foreshadow a much broader pattern of discoveries. This growing body of evidence forced astronomers to revisit one of the central assumptions underlying galaxy formation. According to conventional models, the first galaxies should emerge gradually from tiny density fluctuations seeded shortly after the Big Bang. Dark matter halos would slowly gather ordinary matter through gravity. Gas would cool and collapse into the first stars. Those stars would enrich their surroundings with heavier elements through supernova explosions, allowing subsequent generations of stars to form more efficiently. Over hundreds of millions and eventually billions of years, repeated mergers would build increasingly larger galaxies. Webb's observations suggested that many of these processes may have occurred far more rapidly than expected. Perhaps gas cooled with extraordinary efficiency in the earliest dark matter halos. Perhaps the first generation of stars formed at much higher rates than current simulations allow. Perhaps galaxy mergers proceeded more rapidly in the crowded early universe. Or perhaps entirely new physical mechanisms influenced galaxy formation during cosmic dawn. Each possibility remains under active investigation. One particularly intriguing aspect of Webb's first deep field involved the sheer diversity of galaxies it revealed. Rather than displaying only one type of primitive system, the image contained galaxies spanning an astonishing range of apparent sizes, colors, and morphologies. Some appeared compact and intensely bright. Others displayed elongated or disc-like structures. A few exhibited red colors suggestive of surprisingly evolved stellar populations. Such diversity implied that galaxy evolution may have proceeded along multiple pathways almost immediately after the first stars ignited. The implications extend well beyond individual galaxies. If galaxies assembled more rapidly than expected, they could also produce heavy elements sooner, feed supermassive black holes earlier, and influence the surrounding intergalactic medium more quickly than existing models predict. In other words, many of Webb's seemingly separate discoveries may actually represent different consequences of the same underlying process, an early universe evolving with astonishing speed. Importantly, none of these observations require abandoning the Big Bang itself. The expanding universe remains supported by overwhelming evidence, including the cosmic microwave background, the abundance of light elements, and decades of independent observations. Instead, Webb is challenging the details of what happened after the Big Bang. It suggests that the transition from a hot, nearly uniform universe to one filled with galaxies, stars, black holes, and complex chemistry may have unfolded much faster and more efficiently than scientists previously imagined. The first deep field, therefore, occupies a unique place in the history of astronomy. It was not simply a beautiful image released to demonstrate a new telescope's capabilities. It became the opening chapter of an entirely new era of discovery. Almost every major cosmological puzzle associated with the James Webb Space Telescope can trace its origins back to that first observation. Unexpectedly massive galaxies, ancient stellar populations, rapid chemical enrichment, early supermassive black holes, mysterious little red dots. Each of these discoveries emerged from the same revolutionary ability to observe the distant universe with unprecedented clarity. Perhaps the most remarkable aspect of the first deep field was not any single galaxy within it. It was the realization that our expectations have been too modest. Astronomers built the James Webb Space Telescope, expecting it to confirm decades of theoretical predictions with greater precision than ever before. Instead, its very first glimpse into the ancient universe suggested that reality was more complicated, more dynamic, and more surprising than even the most sophisticated models had anticipated. History often remembers scientific revolutions as dramatic moments when everything changes overnight. In reality, they usually begin much more quietly, with a single observation that refuses to fit existing theories. Webb's first deep field may ultimately prove to be one of those moments. Not because it disproved everything astronomers believed, but because it revealed that the universe still holds secrets hidden within its earliest light. Every galaxy captured in that tiny patch of sky represents a messenger from the dawn of cosmic history, carrying information that has traveled for more than 13 billion years. Together, those ancient galaxies delivered a simple but profound message to modern science. The early universe was far richer, far busier, and far more mature than anyone had expected. And if the very first image from humanity's most powerful space telescope could overturn so many assumptions, one can only wonder what other surprises are still waiting to be discovered in the darkness beyond. For nearly a century, the Big Bang has stood as the foundation of modern cosmology. It is taught in schools, discussed in documentaries, and supported by an extraordinary body of evidence, including the expansion of the universe, the cosmic microwave background, and the observed abundance of light elements such as hydrogen and helium. According to the standard picture, everything we see today, every galaxy, every star, every planet, and every atom, can ultimately trace its origins back to an unimaginably hot and dense state approximately 13.8 billion years ago. But there is one question the Big Bang Theory has never fully answered. What happened before it? Or perhaps even more fundamentally, was there a before it all? For decades, many physicists regarded that question as meaningless because, according to Einstein's equations, space and time themselves began with the Big Bang. If time itself started at that moment, asking what came before would be like asking what lies north of the North Pole. Yet as modern observations continue uncovering unexpected mysteries, from the Hubble Tension and unusually mature galaxies to supermassive black holes that appear impossibly early, some researchers have begun revisiting alternative ideas that once occupied only the fringes of cosmology. These theories do not necessarily reject the Big Bang. Instead, they propose something even more intriguing. Perhaps the Big Bang was not the absolute beginning of everything. Perhaps it was simply the beginning of our current cosmic chapter. One of the oldest alternatives is known as the cyclic universe. The basic concept is surprisingly intuitive. Instead of imagining the universe beginning once and expanding forever, cyclic models propose that the cosmos repeatedly passes through endless cycles of expansion and contraction. After expanding for billions or even trillions of years, gravity, or some other unknown physical process, eventually reverses the expansion, causing the universe to collapse back toward an extremely dense state. Rather than ending in a final singularity, this collapse triggers another expansion, producing a new cosmic era. In this picture, the Big Bang was not the first event. It was simply the latest rebirth in an infinite sequence of cosmic cycles stretching endlessly into both the past and the future. The idea itself is not entirely new. Versions of cyclic cosmology appeared in philosophical traditions long before modern science existed. Ancient civilizations in India, Greece, and elsewhere imagined universes undergoing repeated cycles of creation and destruction. Modern physics, however, approaches the idea very differently. Instead of relying on philosophy, scientists attempt to describe these cycles using mathematics, general relativity, and quantum physics. The challenge has always been explaining how one universe transitions into the next without violating known physical laws. This challenge led physicists toward another fascinating concept, known as the Big Bounce. Unlike the traditional Big Bang model, which begins with an infinitely dense singularity, the Big Bounce suggests that the universe never reaches infinite density at all. Instead, as a previous universe contracts, quantum effects become increasingly important. At incredibly small scales, gravity may behave differently than Einstein's classical equations predict. Rather than allowing matter to collapse into an impossible singularity, quantum gravity could generate an enormous repulsive force that halts the collapse and reverses it. Instead of beginning emerging from nothing, the Big Bang becomes a bounce, a transition between a contracting universe and an expanding one. This idea has become particularly attractive because singularities have long represented one of the greatest unresolved problems in theoretical physics. Infinite density, infinite temperature, and infinite curvature usually indicate that a mathematical theory has reached its limits rather than describing physical reality. Many physicists suspect that a complete theory of quantum gravity will eventually eliminate singularities altogether, replacing them with finite processes that remain physically meaningful. If that happens, the Big Bounce could naturally emerge as one possible description of the universe's earliest moments. Another remarkable proposal comes from the distinguished mathematical physicist Sir Roger Penrose, whose theory is known as conformal cyclic cosmology, or CCC. Penrose approaches the problem from an entirely different perspective. Instead of imagining repeated expansions followed by contractions, he suggests that an infinitely old, ever-expanding universe can eventually become mathematically indistinguishable from an extremely young one. At first glance, this sounds impossible. How can an ancient universe resemble a newborn cosmos? The answer lies in the behavior of time itself. According to Penrose, after unimaginable stretches of time, far longer than the current age of the universe, nearly all matter gradually disappears. Stars exhaust their fuel. Black holes slowly evaporate through Hawking radiation. Eventually, almost nothing remains except extremely low-energy radiation. In such an environment, concepts like distance, size, and even time lose much of their conventional meaning because there are no massive particles left to provide physical scales. Penrose argues that this extremely old universe can then be mathematically transformed into the hot, dense beginning of a new cosmic cycle without requiring a singularity. In this picture, every Big Bang emerges naturally from the infinitely distant future of a previous universe. It is one of the most imaginative ideas in modern cosmology. Naturally, it is also one of the most controversial. Penrose and his collaborators have searched for possible observational evidence supporting conformal cyclic cosmology. They have suggested that subtle circular patterns within the cosmic microwave background may represent faint echoes of violent events occurring in a previous cosmic aeon, such as collisions between supermassive black holes before the last Big Bang. These claims have generated considerable debate. Some analyses argue that the proposed patterns are statistically significant, while many other researchers conclude they can be explained by ordinary random fluctuations within the standard cosmological model. At present, no consensus exists. This situation illustrates an important principle in science. A fascinating theory is not enough. Every cosmological model must ultimately confront observations. That is where the James Webb Space Telescope enters the discussion. Since Webb began observing the distant universe, numerous headlines have suggested that its discoveries prove alternative cosmological models, such as the Big Bounce or conformal cyclic cosmology. These claims deserve careful examination. The truth is more nuanced. Webb has unquestionably discovered galaxies, black holes, and chemical evolution occurring earlier than many theoretical models predicted. It has strengthened existing tensions regarding how rapidly cosmic structures formed after the Big Bang. These observations encourage scientists to reconsider aspects of galaxy formation, dark matter, black hole growth, and perhaps even the earliest stages of cosmic evolution. However, Webb has not directly demonstrated that the Big Bang was preceded by another universe. No observation from the telescope currently provides definitive evidence that a previous cosmic cycle existed. Webb cannot observe before the Big Bang because, according to every existing cosmological model, the light reaching us today was emitted long after the universe became transparent approximately 380,000 years after its earliest moments. Even Webb's extraordinary infrared vision cannot peer through that primordial barrier. So why do alternative cosmological theories continue attracting attention? Because each new anomaly reminds physicists that our current understanding remains incomplete. The Hubble Tension suggests we may not fully understand cosmic expansion. Unexpectedly massive galaxies imply that structure formation may have proceeded more rapidly than simulations predict. Supermassive black holes appear astonishingly early. Ancient spiral galaxies, chemically enriched systems, and quiescent galaxies all seem to mature faster than expected. None of these discoveries proves cyclic cosmology, but together they encourage scientists to remain open to possibilities that once seemed unnecessary. This openness is not a weakness of science. It is one of its greatest strengths. History repeatedly demonstrates that successful theories are refined rather than blindly defended. Newton's gravity explained planetary motion brilliantly until Einstein revealed a deeper description. Classical physics described everyday phenomena perfectly until quantum mechanics uncovered an entirely new microscopic world. Likewise, the standard cosmological model may eventually prove to be an approximation of an even more comprehensive theory capable of explaining today's growing collection of puzzles. Perhaps that future theory will resemble the Big Bang's. Perhaps it will incorporate Penrose's conformal cyclic cosmology. Perhaps it will involve an entirely different framework that no one has yet imagined. Or perhaps the Big Bang will remain fundamentally correct while requiring only modest refinements to our understanding of the universe's first few 100 million years. At present, no one knows. That uncertainty is precisely what makes modern cosmology so exciting. For nearly 100 years, the Big Bang has served as the opening chapter of the cosmic story. The James Webb Space Telescope has not erased that chapter, but it has revealed that many of the pages immediately following it are far more complicated than anyone expected. Every surprising galaxy, every unexpectedly massive black hole, every ancient stellar population, and every unresolved cosmological tension reminds us that the universe still guards profound secrets. Whether the Big Bang was truly the absolute beginning of reality, or merely the latest sunrise in an endless sequence of cosmic cycles remains one of the greatest unanswered questions in science. And perhaps the most remarkable realization of all is this. For the first time in history, humanity now possesses the instruments capable of asking that question not through philosophy or speculation, but through observation. The answers may not arrive tomorrow, or even within the next decade, but somewhere in the ancient light still crossing the universe, the next clue is already on its way toward us. For most of the 20th century, astronomers believed they had finally uncovered the basic ingredients of the universe. Ordinary matter, the stars, planets, gas clouds, and galaxies we can see, was thought to make up everything that existed. But as observations became more precise, an astonishing realization emerged. The visible universe represented only a tiny fraction of reality. Today, according to the standard cosmological model, ordinary matter accounts for only about 5% of the universe. Roughly 27% consists of invisible dark matter, a mysterious substance that exerts gravity but neither emits nor absorbs light. The remaining 68% belongs to something even stranger, dark energy, an unknown form of energy that appears to be driving the accelerated expansion of the universe itself. It is the single largest component of the cosmos, yet no one knows what it actually is. We cannot see it, isolate it in a laboratory, or explain it using the standard model of particle physics. We know it exists only because of the effect it seems to have on the expansion of space. And now, after more than 2 decades of assuming dark energy behaves in a simple and predictable way, new observations suggest that assumption may itself be wrong. If those observations are confirmed, they could force one of the biggest revisions of modern cosmology since the discovery of the accelerating universe. To understand why this possibility is so significant, we need to revisit one of astronomy's greatest surprises. During the 1990s, 2 independent teams of astronomers set out to measure how quickly the universe's expansion was slowing down. According to gravity, every galaxy attracts every other galaxy. Since the Big Bang launched the universe into expansion, gravity should gradually have been pulling everything back together. Scientists expected to measure this gradual deceleration by observing distant type I supernovae, remarkably consistent stellar explosions that act as reliable cosmic distance markers. The observations told a completely different story. Instead of slowing down, the expansion of the universe was speeding up. The farther astronomers looked into space, and therefore back in time, the more obvious the effect became. Something was pushing galaxies apart with increasing strength. This mysterious phenomenon became known as dark energy. Because its true nature remained unknown, cosmologists introduced it into their equations as a placeholder rather than a fully understood physical substance. The simplest explanation came from Albert Einstein. Ironically, Einstein had introduced something remarkably similar decades earlier while attempting to keep the universe mathematically static. This quantity, known as the cosmological constant, represented a uniform energy density built into empty space itself. Einstein later abandoned the idea after Edwin Hubble discovered that the universe was expanding, reportedly calling it his greatest blunder. Yet after the discovery of cosmic acceleration, the cosmological constant suddenly returned, not as a mistake, but as the simplest explanation for the observations. Within the standard cosmological model, dark energy is assumed to behave exactly like this cosmological constant. Every cubic meter of empty space contains the same tiny amount of vacuum energy. As the universe expands and more space comes into existence, the total amount of dark energy increases proportionally, driving expansion ever faster. Most importantly, this energy remains perfectly constant throughout cosmic history. Whether the universe is 1 billion years old or 20 billion years old, dark energy behaves exactly the same way. For more than 20 years, this assumption became one of the foundations of modern cosmology. Then astronomers began collecting vastly more precise data. One of the most ambitious projects ever undertaken to study the large-scale structure of the universe is the Dark Energy Spectroscopic Instrument, better known as DESI. Installed on the Hubble Telescope in Arizona, DESI is designed to measure the positions and distances of tens of millions of galaxies and quasars. By creating the largest three-dimensional map of the universe ever assembled, scientists hope to reconstruct how cosmic expansion has changed throughout billions of years of history. The scale of the project is extraordinary. Every clear night, DESI observes thousands of galaxies simultaneously using thousands of robotic optical fibers that automatically position themselves with astonishing precision. Over time, this enormous dataset allows astronomers to trace subtle patterns left behind by sound waves that propagated through the infant universe shortly after the Big Bang. These patterns, known as baryon acoustic oscillations, serve as an enormous cosmic ruler stretching across billions of light years. By measuring how this ruler appears at different epochs, scientists can determine how the expansion of the universe has evolved over time. Recent analyses combining DESI observations with other cosmological datasets have produced results that immediately attracted worldwide attention. While the standard cosmological model still provides an excellent overall description of the universe, some analyses suggest that the data may fit slightly better if dark energy is not perfectly constant after all. Instead, its influence may have changed gradually over cosmic history. This possibility is sometimes described using the phrase dynamic dark energy. Rather than representing a fixed property of empty space, dark energy could evolve with time, slowly strengthening or weakening as the universe ages. Some theoretical models describe this behavior using a hypothetical field known as quintessence, a form of energy that changes gradually rather than remaining perfectly constant. If true, the implications would be enormous. The standard cosmological model, often called lambda CDM, derives its remarkable predictive power from the assumption that dark energy behaves exactly like Einstein's cosmological constant, represented by the Greek letter lambda. Countless calculations concerning the age of the universe, the growth of galaxies, and the evolution of cosmic structure depend upon this assumption. If lambda is no longer truly constant, many aspects of modern cosmology would require careful re-examination. That does not mean everything would suddenly become wrong. The Big Bang itself would remain strongly supported. The cosmic microwave background would still exist. The expansion of the universe would still be real. The evidence for dark matter would remain overwhelming. But the details describing how the universe evolved during the past several billion years might require important revisions. Naturally, astronomers have responded with considerable caution. Science has encountered many intriguing hints that eventually disappeared as additional observations accumulated. The current DESI results are exciting precisely because they are suggestive, not conclusive. While some combinations of observational data appear to favor evolving dark energy, the the statistical significance has not yet reached the level required to claim a discovery. Future DESI data releases, along with observations from projects such as the Euclid mission and the Nancy Grace Roman Space Telescope, will provide much stronger tests over the coming years. This careful skepticism is essential. Extraordinary conclusions require extraordinary evidence. Nevertheless, the possibility alone has energized theoretical physics. If dark energy changes over time, entirely new forms of physics may be required. Some researchers explore modifications to Einstein's theory of general relativity. Others investigate new quantum fields permeating space. Some models connect dynamic dark energy with the mysterious inflationary expansion thought to have occurred fractions of a second after the Big Bang. Others speculate that dark energy may interact with dark matter in subtle ways that current theories have overlooked. Interestingly, this growing uncertainty arrives alongside an expanding collection of other cosmological puzzles. The Hubble tension continues suggesting that the universe expands differently depending on how we measure it. The James Webb Space Telescope has revealed galaxies, supermassive black holes, and chemical evolution appearing surprisingly early in cosmic history. The axis of evil hints at unexpected large-scale alignments in the cosmic microwave background. Gigantic cosmic structures challenge assumptions about the largest scales of organization in the universe. None of these mysteries necessarily point toward the same solution. Yet together, they remind scientists of an important truth. The standard cosmological model remains extraordinarily successful, but it is almost certainly incomplete. Perhaps evolving dark energy will eventually prove to be nothing more than a statistical fluctuation that disappears with additional data. Perhaps DESI is providing the first glimpse of entirely new physics operating across the largest scales of the cosmos. Or perhaps the final explanation will be something no one has yet imagined. History suggests that the greatest scientific revolutions often begin with small inconsistencies hiding inside otherwise successful theories. Tiny irregularities in Mercury's orbit eventually revealed general relativity. Subtle anomalies in blackbody radiation gave birth to quantum mechanics. Today, one of the biggest questions in cosmology may depend upon something equally subtle: the possibility that the mysterious force driving the expansion of the universe is not constant after all. If future observations confirm that dark energy evolves with time, the consequences would extend far beyond a single equation. They would reshape our understanding of the universe's past, alter predictions about its future, and perhaps even change our answer to the oldest question in cosmology. Not just how the universe began, but how it has been evolving ever since. After decades of believing we had identified the dominant ingredient of the cosmos, we may once again discover that the universe is far stranger than we ever imagined. For nearly 100 years, the Big Bang has served as the foundation upon which modern cosmology has been built. It has explained why galaxies are moving away from one another, why the universe is filled with the faint glow of the cosmic microwave background, and why the lightest elements exist in precisely the proportions we observe today. It has survived countless experiments and decades of increasingly precise observations, becoming one of the most successful scientific theories ever developed. Yet history teaches us an important lesson. The greatest scientific revolutions rarely occur because an old theory is completely wrong. More often, they happen because a successful theory turns out to describe only part of a much larger picture. Newton's laws were not discarded when Einstein introduced general relativity. They remained extraordinarily accurate within their proper limits. Likewise, quantum mechanics did not erase classical physics. Instead, it revealed a deeper layer of reality operating beneath it. Today, astronomy may once again be approaching one of those extraordinary moments. Not because the Big Bang has been disproven, but because the universe is beginning to reveal details that our current cosmological framework struggles to explain. Throughout this journey, we have explored a remarkable collection of discoveries. The James Webb Space Telescope revealed galaxies appearing far larger and more mature than expected only a few 100 million years after the Big Bang. It uncovered supermassive black holes whose enormous masses seem almost impossible to reconcile with conventional growth models. It detected surprisingly high metallicity in ancient galaxies, suggesting that multiple generations of stars may have lived and died with astonishing speed. It found quiescent, red, and dead galaxies existing billions of years earlier than many simulations predicted. We examined the Hubble Tension, where two of the most precise methods ever developed for measuring the universe's expansion continue producing irreconcilable answers. The James Webb Space Telescope has only begun its scientific mission. Every observing cycle brings deeper surveys, more detailed spectroscopy, and entirely new windows into cosmic history. Many of today's candidate galaxies will soon receive much more precise measurements. The mysterious little red dots continue to be studied in extraordinary detail. The earliest supermassive black holes are revealing clues about their formation. Every new observation has the potential either to strengthen existing mysteries or to resolve them completely. And Webb is only one part of a much larger scientific revolution. The Vera-C Rubin Observatory, equipped with the largest digital camera ever constructed for astronomy, is beginning an unprecedented survey of the southern sky. Night after night, it will repeatedly image billions of galaxies, discovering countless supernovae, mapping dark matter through gravitational lensing, identifying new near-Earth asteroids, and providing an extraordinary record of how the dynamic universe changes over time. Its data will transform nearly every area of observational astronomy. Meanwhile, the Euclid Space Telescope is creating one of the most detailed maps of dark matter and dark energy ever attempted, helping scientists understand how cosmic structure has evolved over billions of years. The Nancy Grace Roman Space Telescope, expected later this decade, will combine an enormous field of view with Hubble-like resolution, allowing astronomers to study galaxy formation, dark energy, and exoplanets on an unprecedented scale. Ground-based observatories, radio telescopes, gravitational wave detectors, and next-generation cosmic microwave background experiments will all contribute their own pieces to the puzzle. Never before in human history have so many revolutionary instruments been exploring the universe simultaneously. That is why many cosmologists believe the next 5 to 10 years could become one of the most important periods in the history of astronomy. Some of today's mysteries may disappear. Others may become even stronger. Entirely new anomalies may emerge that no one has yet imagined. This is exactly how science progresses. Not through certainty, but through curiosity. Not by defending old ideas at all costs, but by allowing nature itself to decide which theories survive. It is also important to remember what these discoveries do not mean. They do not prove that the Big Bang never happened. They do not demonstrate that everything scientists have learned over the past century is incorrect. The evidence supporting an expanding universe, the cosmic microwave background, and primordial nucleosynthesis remains extraordinarily powerful. Any future theory must still explain these observations at least as successfully as the current model does. What may change is something more subtle, and perhaps even more fascinating: our understanding of what happened after the beginning. Perhaps the Big Bang represents only one chapter in a much larger cosmic story. Perhaps dark energy behaves differently than we currently believe. Perhaps gravity itself operates in unexpected ways on the largest scales. Perhaps the first stars and galaxies formed under physical conditions unlike anything we have ever observed in the modern universe. Or perhaps nature is preparing to surprise us with an explanation no one has yet conceived. History suggests that the universe has a habit of exceeding human imagination. Every generation believes it has nearly completed the cosmic puzzle. Then a new telescope is built, a new observation arrives, and suddenly the picture becomes larger than anyone expected. When Galileo first turned his telescope toward Jupiter, he discovered moons orbiting another world, forever changing humanity's place in the cosmos. When Edwin Hubble revealed that the Milky Way was only one galaxy among billions, our universe expanded beyond imagination. When astronomers discovered that cosmic expansion was accelerating, they realized that most of the universe consists of something completely unknown. Now, the James Webb Space Telescope is once again reminding us that the cosmos still holds profound secrets waiting to be uncovered. Perhaps decades from now, future generations will look back on this period as the moment when astronomy entered a new era. Not because one famous theory collapsed overnight, but because a growing collection of observations quietly revealed that reality was richer, deeper, and more mysterious than anyone had dared to imagine. The story of the universe has never truly been about certainty. It has always been about discovery. And if the past century taught humanity how the universe began, the next decade may finally begin teaching us something even more extraordinary. What really happened in the moments that followed, and whether the story we call the Big Bang was the beginning of everything or simply the beginning of the next chapter.